So I'm going to open up my web browser. This is the tool we're going to be using throughout basically the entire course, is Google Colab. So if we come here to colab.research.google.com. If you're unfamiliar with Google Colab, check out the Colab overview, or if you just go to colab.research.google.com, you can go to the examples tab here, and you can open up a whole bunch of different tutorials to go through and learn about Google Colab. If you're just starting out, I'd check out Overview of Collaboratory Features or the Markdown Guide. But as I said, if you want another overview, check out the overview video because we're going to be using Colab a whole bunch throughout this course. So let's get started. I'm going to open up a new notebook here because we're going to, I don't know if you can hear that, but I'm rubbing my hands together because I'm so excited. We're going to get hands-on with TensorFlow. So some of the most fundamental functions of TensorFlow. And let's give our notebook a title here. So let's go 00 TensorFlow Fundamentals. The reason I'm doing 00 at the start is because we're going to, by the end of this course, have probably about 10 or so of these notebooks. So the 00 at the front just lets us know what order they come in. So TensorFlow Fundamentals, and now let's put in here, in this notebook, we're going to cover some of the most fundamental concepts of tensors using TensorFlow. Beautiful. And we can put a little hashtag at the front. And then what I did there was I did Command MM and turned it into a markdown cell. And then if I press Shift and Enter, we get another code cell here. Beautiful. And so to enable us to write code, we're going to have to connect here. So just press the Connect tab there. And let's get a little outline of what we're actually going to do. So more specifically, this is what I do with most of my notebooks. Whenever I come to something before writing code, you're going to hear me say write code as much as possible. But I just like to give myself a little bit of an outline so I know the direction of where I'm heading. So we're going to cover, what do we have? Introduction to tensors. We might as well get some information from tensors. If none of this makes sense, don't worry. We're going to code it up by hand. Manipulating tensors. So changing the information that's stored within tensors. And then we're going to go tensors and NumPy. If you've ever used NumPy, TensorFlow you'll find has very, very similar features to NumPy. Using @tf function, which is a way to speed up your regular Python functions in TensorFlow. Because remember, the whole premise of using TensorFlow is so that we can use GPUs with TensorFlow or TPUs to do faster numerical computing. That's what we're after here. And at the end, we're going to have a few exercises to try for yourself. Alrighty, let's just jump straight in. I'm going to put another little heading here, Introduction to Tensors, and then I'm going to press Command MM to turn that into Markdown. Now for another cell here, I'm going to press Command MB. Oh, I didn't press Escape while I had this cell highlighted. So Escape, Command MB will give me a new cell. Now I'm saying Command, however, if you're on Windows, it's probably Control. Because I'm on a Mac, it's Command for me. So the first thing to do is to use TensorFlow is that we have to import TensorFlow. Now, I want you to try and follow along as much as you can with these videos, right? When I'm writing code, I want you to be writing code by my side. It's like we're partner coders here. And if you can't keep up because I'm writing a little bit too fast, that's all right. I've had a lot of practice writing TensorFlow code. And so, again, I've spelled TensorFlow wrong. Maybe you'll catch my errors before I do. If you need to slow down the video or watch something again, that's perfectly fine. I'm probably going to need to slow down my code so I don't write as many typos. So this is how we're going to import TensorFlow. TensorFlow becomes the alias tf in Python. Tf is basically universal. You can put it as what you want, but use tf, trust me. And then I'm going to use print tf.__ here, version, to check what version of TensorFlow we're using. If you're using Google Colab, you should be using TensorFlow 2 point something. I'm currently using 2.3.0. By the time you watch this video, there may be a newer version of TensorFlow, but everything that we do in this fundamentals notebook should still work perfectly fine. So look at that. We've already got TensorFlow ready to go. Now let's jump in and create our first tensor. Creating tensors with tf.constant. Now you're going to see there's a few different ways to create tensors, but in general, you actually probably won't create many tensors yourself. This is because TensorFlow has many built-in modules, as we'll get familiar with throughout the course, such as tf.io and tf.data, which are able to read in your data sources, such as if you had a whole bunch of different images, and automatically convert them into tensors, as long as you write the code for that, that is. And then later on, our neural network models will process these tensors for us. But for now, we want to get familiar with tensors themselves, so let's start creating tensors. And what I've written here is the word scalar, which you might not be familiar with for now, but that's all right. We will learn what that is. Beautiful. So when we create a tensor with tf.constant, we get this. We return this. It says tf.tensor. It has a shape that's empty. The data type is int32. And in NumPy, this value is 7. So again, NumPy and TensorFlow are quite intertwined. Now, if we want to get the information or the doc string for what this function is, in Google Colab, you can press Command-Shift-Space. If you're on Windows, it may be Control-Shift-Space whilst you're in the function. And here we go. Creates a constant tensor from a tensor-like object. Or, if we just wanted to search, TensorFlow tf.constant. This is what I want you to get really familiar with, is just searching up something like this. And then going into the documentation, tf.constant, yes, creates a tensor, a constant tensor from a tensor-like object. All right. And then we go here, example use cases. So oftentimes, if I'm not familiar with something in TensorFlow, I'll just search it up like this. I'll find the example code here, and then I'll just rewrite that code in the notebook. But let's keep going. Let's keep writing. All right. How about we check the number of dimensions of a tensor? This is another important concept that we're going to get familiar with as we go along. So ndim stands for number of dimensions. You might be wondering, Daniel, what's ndim? So we've got scalar ndim.ndim. Number of dimensions. So 0. Number of dimensions. What does that mean? Well, let's keep going. We'll come back to that in a second. How about we create a vector? So we've got a weird word here you might not be familiar with, scalar. Now, another word you're going to come across quite often in the deep learning world is vector. So let's see what they are. Again, this is the structure of what I want to go through, is write the code first and then go through the concept, or concept code, concept code, concept code. Vector. Let's see how these two differ. We have scalar, which is a TF tensor, has shape, which is blank, dtype int32, NumPy 7. Okay. Now we created a vector, and now we passed it a Python list to tf.constant, which has tf tensor shape equals 2, maybe that's because there's two items or two objects within this list. The data type is int32, and the NumPy array version is 1010, so the same as this, and the d type is int32 for the NumPy array version. Okay. All right. Now, what about if we check the dimension of our vector? So we go vector.ndim. What do you think it'll be? 1. Okay. So is that because this shape is empty, maybe 0 came from that, and this shape has 1 element, so maybe that dimension came from that. Well, let's keep going. Create a matrix. So a matrix has more than 1 dimension. Again, if these terms are unfamiliar for now, we're going to get very familiar as we go along. So a matrix, we want to go 10, 7, and then 7, 10. Two of my favorite numbers. If you ever played poker, my favorite hand is 10, 7. Matrix. Let's see what this is. Okay. tf.tensor shape equals 2, 2. Does that make sense? 2 items here, comma, 2 items here. Okay, yep, that makes sense. dtype is int32, so these are integers. And then the NumPy version is just the same thing here with a data type of int32. Wonderful. Now, before I write the code, I want you to have a think. If we write matrix.ndim, if the vector had a dimension or number of dimensions as 1, and if a scalar had number of dimensions as 0, what do you think the matrix will be? 3, 2, 1. Boom, 2. Okay, so I'm starting to see the number of elements in shape is starting to relate. That's where I'm drawing my own pattern between ndim. All right, now let's create another matrix, but this time we're going to try out, how about we try and specify the data type? So if we go here, dtype, that's what we want to try and use. So let's try and do that. Create another matrix. Now another matrix equals, how can we do this? tf.constant. What do we want to put in? What are your favorite numbers? I'm going to do my favorite numbers again. 10.7. Oh, you might have noticed something different about this one already. So we have a dot after our number. And if you're writing in Python code, what does a dot typically mean after an integer? And 8 and 9. That'll be nice and simple. And then what did we say we were going to do? We're going to use the dtype parameter, float 16. So we're going to specify the data type with dtype parameter. Now the reason I'm getting you familiar with the dtype parameter is because by default, if we create a tensor with tf.constant, we get the data type int32. So this is known as 32-bit precision. So if we go here, 32-bit precision, which is a quite, I'm not going to dive too deep into that. The concept is the higher the number of precision, the more exact these numbers are stored on your computer. So if we do float 16, it's a lower number than 32. So that means storing these numbers or storing this tensor on our computer's memory is going to take up less space. The reason I'm getting you familiar with this is because if you get a data type error in the future of your tensors being the wrong data type, you can manipulate them using the dtype parameter. So let's have a look here. Another matrix. What does this come up as? There we go. Boom. tf.tensor. The shape is 3 by 2. Oh, okay. So this is rows, columns. So we have 3 rows. 1, 2, 3. And because we've specified the data type as float 16, we get dtype equals float 16, which makes sense. And our integers here have a dot after, so they're actually floats. And then the same goes for our NumPy version of our tensor matrix. So what do you think the number of dimensions is of another matrix? So if we come back up here, what was our number of dimensions of our matrix here? And our vector? And our scalar? We've just created another matrix. If we were to go another matrix dot ndim, what do you think the output would be based on the shape here? Let's find out. Boom, it's still 2. So even though the shape here is different, the total number of dimensions, which is the element, I'm really starting to notice a pattern here. The total number of dimensions is how many elements is in the shape. Okay, I've got that down. How about why don't we see, how might we increase this number of dimensions? I know how we can do it. Let's create a tensor. So typically with this nomenclature, a scalar will have no dimensions, a vector will have 1 dimension, a matrix will have 2 dimensions, and a tensor will have, we'll see what that has. Let's go tensor. Can't reveal all my tricks before we try and code them out. Remember, if in doubt, code it out. Now, to create these, you're going to have to get pretty fancy with where you put your commas. So while I'm creating this, if you're finding that you're like, Daniel, I can't really follow along, that's okay. Just wait till I'm finished here, watch what I'm doing, and then you can pause the video, replicate what I've got, and then we'll run it together, all right? Boom. And then this one has to have 2. Now you see how tedious it is creating tensors from, like, with your hands? I mean, this is why it's so helpful for TensorFlow to create tensors for us, as we'll see in future modules. Hopefully, I've got all these little square brackets and commas in the right place. So if we look at our tensor, Shift and Enter, what's it going to output? Ooh, hello. We have how many more elements in the shape? We have an extra one. Okay, so there's 3. So 1, 2, 3, yes, 2. So 1, 2, and then 3 again. 1, 2, 3. Ah, beautiful. Now, if we wanted to check the number of dimensions of this tensor, what do you think it would be? I think you might know this one. Tensor.ndim. Boom, 3 dimensions. Wonderful. Now, the important thing to note is that although we've given these different names, tensor, matrix, vector, scalar, is that all of these in TensorFlow, throughout the entire course, we're basically going to continually refer to these, no matter if they're a 3-dimensional tensor or if they're a 2-dimensional tensor, which is a matrix, we're going to consistently refer to them as tensors. So if you're getting confused when I say matrix or tensor, chances are it's the same thing throughout this course. And so, how about we write down some little definitions? What we've created so far. Nice and simple. So scalar. A scalar is a single number. A vector is a number with direction. So e.g. wind speed and direction. A matrix is a 2-dimensional array of numbers. Wonderful. And a tensor is an n-dimensional. Now, when you see n, so the n here for n dimensions stands for number. Whenever you see n, it's often referred to as number of something. So n-dimensional means it could be 0-dimensional, or it could be up to 1,000 different dimensions or more. Array of numbers, where n can be any number. A 0-dimension, as we said before, dimensional tensor is a scalar, and a 1-dimensional tensor is a vector. Beautiful. So that's what we've created so far. We've created our first 5. Have we created 5? 5 different tensors. Now, in the next video, we've created them with tf.constant. Let's have a look at another way of how we can create tensors, this time with tf.variable. I'll see you then. So we've created some of our very first tensors, which is so exciting, using tf.constant. Let's look at how we might do it with our tf.variable. So, again, little tip here, if you want to create a new cell in Colab, you can press code or text. But most of the time, I just do the shortcut, so escape, command MB. Boom. But I'm going to put a text cell here, and I'm going to put a little heading here, creating tensors with, and then if we go backtick, tf.variable. Wonderful. So, let's see what type tf.variable is here. We could jump straight into it, but we want to have some practice looking up the documentation. So TensorFlow tf.variable. Now the first probably, I reckon at least 100 times you read something in the documentation, especially if you're new to TensorFlow, it probably won't make too much sense. But once you've had a fair bit of hands-on practice, you'll start to get used to it. So tf.variable, look how many different parameters we have here, far out. Traditionally, like in practice, I don't really read all of these. I go down and I like to see things being used. So here we go, tf.variable 1 dot, so that should be a float, yes, v assign. What's that? Well, we could keep going through that, but let's get hands-on. Again, if you want more about something from TensorFlow, look it up in the documentation, come through these code examples, write them out for yourself, and just check what the inputs and outputs are of the code that you're writing. So let's go back. tf.variable. How might we create the same tensor with tf.variable as above? This is going to be, as you might have guessed by the name, a changeable tensor. What's that? tf.variable 10.7. So remember up here, we created a vector of 10.10. Oh, I said 10.10, 10.7. There we go. That's what we want. 10.7. Now we're doing it here. And let's have a look at this one. Unchangeable tensor. tf.constant. And then we want 10.7. Wonderful. We're going to write these out. We're going to visualize them. Unchangeable tensor. Did I type out the variable names correctly? Yes, I did. Wonderful. Okay, now we get some different outputs. So the first one here is our changeable tensor that we created with tf.variable. So tf.variable, wonderful, shape, okay, 2, DType. In 32, we've seen that before, NumPy, okay. Now this is tf.tensor, which is the unchangeable tensor that we created with tf.constant. You see these are output in order here, so this one first, and then this one, which is exactly what we've seen above before. Shape 2, DType equals int32, NumPy array is of that. Wonderful. What do you think might happen if we tried to change one of the elements in our changeable tensor? It's all right if you're not sure, but let's try change one of the elements in our changeable tensor. So changeable tensor 0, or let's try to index it first. What comes up is NumPy 10. So we've got the first value here, so the 0 index. So what if we wanted to set that? We want to make a tensor which is 7.7. So we want to set that first number, 10, to be 7 also. What happens if we try to visualize it here? Okay, we get an error. Resource variable object does not support item assignment. Okay, what if we go back to this documentation? So tf variable, they've created one here, similar to how we've created ours, but they've only got one element, which is a scalar. Then they've used v.assign. All right, and then it's changed from 1 dot to 2 dots. So what if we tried that? So let's come back here. How about we try dot assign? All right. Changeable tensor, and the 0th element, dot assign, and then we want to change it to 7. Just 7. What do you think will come out here? Let's have a look. Ooh, wonderful. There we go. All right. So how about if we tried to change a value in our tf.constant tensor, or our unchangeable tensor? Now, let's try change our unchangeable tensor. Let's just try to do the same change. Make it simple. Unchangeable tensor, 0th element. Well, first we'll index it as well, just to check. Same output here, NumPy 10. And what if we go equals 7? What happens there? Oh, object does not support item assignment. Okay, so similar error to what we got up here. Oh, that's okay. We know the fix. We can just go assign 7. Oh, get that bracket back up on there. And then we'll check out the unchangeable tensor. Oh, another attribute error. TensorFlow Python framework ops eager tensor. Object has no attribute assign. So what do you think is going on here? We've got a changeable tensor, which is a tf variable, and an unchangeable tensor. Where our tf variable is changeable using the assign attribute, whereas our unchangeable tensor, which kind of makes sense if it's name, doesn't change even when we use the assign. Now, you might be wondering, why can we change some tensors and why can't we change others? Well, it comes down to behind the scenes, when we're writing neural network code, we might want some tensors for their values to be changed, whereas we might want some tensors for their values not to be changed. So there's a variable tensor and there's a constant tensor. Now, again, we're going to reiterate the fact that a lot of the times you won't have to make the decision between using a variable tensor or a constant tensor. The decision will be made for you behind the scenes when TensorFlow creates tensors for your neural networks. But we're going to get very hands-on with that. And so speaking of TensorFlow creating tensors for our neural networks, let's have a look in the next video, which is going to be creating random tensors. Woohoo! That's exciting. I'll see you then. So we've seen how to make tensors with tf.constant and tf.variable. Let's see how we might create random tensors. So actually, I'll make that a size 3 heading. And I just want you to I'll point out something here that I've added to the last little section of code that we run. This is going to be a trend throughout the course, is that if there's like a little tidbit that you should be aware of, I'm going to use this key emoji and add a little note there. So rarely in practice will you need to decide whether to use tf.constant or tf.variable to create tensors, as TensorFlow does this for you. However, if in doubt, use tf.constant and change it later if you need. So that's a little tidbit going forward. So if you ever see the key emoji with something coming after it throughout this entire course, throughout any of the notebooks that you use and the GitHub and whatnot, that's just a little tidbit to take note of for later. But let's get hands-on creating random tensors. So random tensors are tensors of some arbitrary size which contain random numbers. You might be wondering, why on earth would I ever want to create a tensor? Where's an example of one of our tensors? Like this, filled with random numbers. And I have a great illustration to show you. So let's go to our keynote slide here. This is what neural networks use to initialize their weights, in other words, the patterns, that they're trying to learn in our data. So if we imagine this diagram here, we have our inputs. Say we had pictures of food that we're trying to classify into ramen or spaghetti. We might turn that into tensors. We'll see how to do this in a future project. So this is our numerical encoding of our images. Then we might pass that numerical encoding to the input layer of our neural network. Then our neural network might learn representations which are called patterns, features, or weights, then output those representation outputs, and then we convert them into something that we can understand rather than just tensors. But where does a neural network get these representations from? Well, in the beginning, it's going to initialize itself. Initialize is another common word you'll hear in deep learning. Initialize just means start with. Initialize its weights or the patterns it knows with random weights or random tensors. So this would be a random tensor to begin with. And then, as it sees different examples of photos of ramen and spaghetti, it's going to update its representation outputs. In other words, start to tweak these random weights and patterns to better suit our data. If we go through again, we're going to repeat this cycle with more and more examples. So if we imagine the float here, we've got images, we numerically encode them, our neural network initializes itself with random weights, in other words, a random tensor, and then as we start to show it more examples of what photos of ramen and spaghetti look like, it starts to tweak these random weights to be better adjusted to the patterns that are in our images so that our representation outputs line up better with our desired labeled outputs. So maybe in the beginning it gets these images, these two here, wrong, but then as it keeps going, it starts to learn them and it starts to get them right, like these two here. So let's go back. That's a brief overview of how a neural network learns, but that's the context of where you might use a random tensor. So how might we create a random tensor? So let's create two random but the same tensors. Now, before we even write any code, we go how to create random tensors with TensorFlow. TensorFlow.random.uniform. Wonderful. So we could go through that, or we could start to write the code. Seriously, when I don't know something, that is the type of search that I will put into Google and look up. As much as I'm trying to teach you TensorFlow itself, I'm trying to teach you how to search for answers to solve your own problems. Because at the end of the day, I can only show you so much. But let's create random1, which is going to be tf.random.generator.fromSeed42. What is a seed? So the set seed for reproducibility. So we'll see what the random seed means in a minute. If you've ever used NumPy, it's very similar to NumPy's random seed. So random1 equals random1.normal. I want you to guess if we put in the shape parameter here. So if we come here, go to this first one, random uniform, shape. We've got random normal, shape 3, 2. What shape will our tensor be if we were to press Shift and Enter? tf.tensor, shape 3, 2. Now, we've used normal here, but this is uniform. What's the difference? So output random values from a uniform distribution. What is a uniform distribution? Here we go. wolfram.com. A uniform distribution, sometimes also known as a rectangular distribution, is a distribution that has constant probability. Whoa. So oftentimes when I read stuff like this, it takes me a long time to grasp it. If you're the same, I want you to realize that that's not necessarily a problem. It's because in practice, when you're writing these random tensors, again, a lot of it is done behind the scenes for you. What I want you to get familiar with is writing as much code as possible, like we've done here, and then starting to see what the outputs of that code is. The more and more you do it, the more familiar you will get with it. So let's create another one. Maybe we'll come up here, random2 equals tf random generator from seed 42, random2 equals random2.normal shape equals 3, 2. You might be wondering, Daniel, you've just looked up uniform and you haven't done anything with it. So what is normal? Well, great question. So what is TensorFlow random normal? tf.random.normal. Outputs random values from a normal distribution. Okay, tf random normal shape. All right, what is a normal distribution? See how we're sort of just pulling the thread here? This is what I do with any problem that I'm working on. A function that represents the distribution of many random variables as a symmetric bell-shaped graph images. Okay, so that's the normal distribution. Again, you can look into this more if you want, but we're going to be practicing writing more random tensors. So are they equal? Random 1, random 2, and now we'll use this equality operator to compare the two. Random 1 equals random 2. Are these equal? Let's have a look. What do you think? Are they going to be equal? Oh, yes we do. We have random 1, remember these come out in order, and then random 2. And so they've come from a normal distribution. This equality operator is this last one here, which is saying that the top left element is matching this top left element, true. The top right is matching here and here, so that comes out true. And then we get the same for the rest of the array. Beautiful. So I want you to know that the random tensors here, although these appear pretty random, these numbers, they're actually pseudo-random numbers. So they appear as random, but they really aren't. That's because we've set the seed here. Setting the seed says something along the lines of, hey, TensorFlow, create me some random numbers, but flavor them with x, where x is the seed. So what do you think would happen if we changed the random seed to my favorite number, which is 7? I have a dog called 7. She's beautiful. What do you think will happen here? We get some slightly different random outputs, but they're still the same between random 1 and random 2. Okay, we've seen how to briefly create some random tensors, and I mean, if we go how to create random tensors with TensorFlow, there's going to be a whole bunch of more different ways. But if we had our random tensors, or if we had just non-random tensors, what if we wanted to shuffle the order that the variables appear in here? Let's have a look at that in the next video. In the last video, we checked out how we can create some random tensors, and we tied that back to the concept of when a neural network starts to learn, if it wants to learn patterns in some sort of data set, it starts off with random patterns and then slowly adjusts them as it continually learns on more and more examples. So if we come back here, in this video, let's see how we might shuffle the order of, what should we call it, elements in a tensor. All right. Why would you want to shuffle the order of elements in a tensor? Let's go back to our example here. So let's say we were working on a food image classification problem, and we had 15,000 images of ramen and spaghetti. Let's keep it nice and simple. And the first 10,000 images were all of ramen. And the last 5,000 images in our folder, like they're in order, so the first 10,000 are all of ramen, and the last 5,000 are all of spaghetti. Now, this order could affect how our neural network learns. So if it goes through these images in order, it might start to adjust its random weights too much so to the images of ramen, because if it goes through 10,000 images of ramen, it's like, okay, well, I only have to learn what ramen looks like. It doesn't know that it has to also learn what spaghetti looks like until it goes to the last 5,000 images. So instead, it might be a good idea to just mix up all the images in our folder so that they basically have no order at all. So we might have ramen, 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 spaghetti, spaghetti, ramen, spaghetti, ramen, spaghetti, ramen. And then the neural network can be fed different examples of different images and adjust its internal patterns or weights, the random tensors it got initialized with, to learn both types of images at the same time. Let's go back to our Colab notebook and let's see how we might shuffle a tensor. So we go shuffle a tensor. So this is valuable for when you want to shuffle your data so the inherent order doesn't affect learning. Now, what we might do is create another tensor. We'll get some practice creating tensors here. Not shuffled equals tf.constant. And then we might just create a very similar tensor to what we created above, 10, 7, my favorite combination of numbers, my favorite poker hand. And there we go. And 2, 5. Why not? There we go. So a little test here is if we did not shuffled .ndim, what do you think that's going to output? Well, let's find out. 2. Okay. Why might that be? Not shuffled. Because it has a shape of 3, 2. So there's 2 elements in the shape attribute. Beautiful. So let's see how we'll shuffle this. Maybe if we just go how to shuffle a tensor in TensorFlow. tf.random.shuffle. Okay, beautiful. So randomly shuffles a tensor along its first dimension. tf random shuffle seed equals none value. Okay, there's an example output. Let's try it out. So the value, what's value? This is how I read the documentation. So the arguments. So the value is a tensor to be shuffled. That's what we want. And the seed could be a Python integer used to create a random seed for the distribution. C random.setSeed for behavior. Okay, let's get hands-on with this. So shuffle our non-shuffled tensor. So let's go tf.random.shuffle. And then, oh, look at that. The doc string appears for us. If we wanted that on our own, we could press Command-Shift-Space. See, I'll come, In Colab, it automatically, sometimes the doc string just automatically comes up if you're just chilling in here. But we can press Shift Command Space, or if you're on Windows, Shift Control Space. There we go. We just get the exact information from the TensorFlow documentation. How handy is that? So let's pass it. What does it take? Args, value, a tensor to be shuffled. Let's pass it in not shuffled. Okay. What do you think is going to happen here? Well, let's find out together. Boom. Okay, look at that order there. So if we get 10, 7, 3, 4, 2, 5, and now the order's changed up here. Okay, so there's still 2, 5, still 10, 7, still 3, 4. Okay, what it's done is if we come back up here, randomly shuffles a tensor along its first dimension. So if we look at not shuffled, it's got a dimension of 3 times 2, which is 1, 2, 3 elements. So it shuffled it along its first dimension, which means it shuffled it along this dimension here. So the 3, 1, 2, 3. So it means that the elements in the second dimension, which is 10, 7, 3, 4, 2, 5, have stayed in order, but they've been shuffled around. So 10, 7 was at the top, but now it's in the middle. 3, 4 was in the middle, but now it's at the bottom. And 2, 5 was at the bottom, but now it's at the top. Okay, now what if we were to run this cell again? I want you to take note. Actually, let's copy this. So copy that. And I'm going to add another code cell here. I'm going to run this cell here. Okay, 10, 7, 3, 4, 2, 5. Same as before, but what if we run it again? 10, 7, 2, 5, 3, 4. Okay, different order. Notice how every time I run it, it's a different order. And I mean, there's only 3 elements here, so sometimes you're going to get the same. Now, what if we were to put seed equals 42? Because if we come here, a Python integer, seed, used to create random seed for the distribution. What happens if we do that? Seed equals 42. Seed equals 42. We get still different results. So what if we did tf.random.set_seed 42? Okay. 10, 7, 3, 4, 2, 5. 10, 7, 3, 4, 2, 5. 10, 7, 3, 4, 2, 5. Okay. 10, 7, 3, 4, 2, 5. Now we're getting the same order. That's quite confusing. So how might we figure this out? If we come back here, seed, we set that to 42, but we didn't get the same results. So seed, it says here, used to create a random seed for the distribution C, tf random seed for behavior. Okay, so let's click on that. Here we're kind of pulling the thread of what our problem is. We're trying to figure out how to set random seeds or random operations in TensorFlow. So operations that rely on a random seed actually derive it from 2 seeds, the global and operation level seeds. So I think this one might be the global level seed, and this one might be the operation level seed because it's a part of an operation here. That's my intuition. Now, its interaction with operation level seeds is as follows. Okay, so we've got 4 rules here. I'm not going to read these out, but what I want to do is put this here, and I want you to start exploring or start practicing. So this is your homework for this lesson, so this one can be here. If you see this symbol here, this means exercise. So exercise, we're going to go read through TensorFlow documentation on random seed generation and practice writing 5 random tensors and shuffle them. That's your takeaway for your homework for this lesson. It's all right. If you want to skip over that and just go straight to the next video, you can. But to really understand the concept of TensorFlow creating tensors, just go through and try create maybe 5 different tensors here with tf.constant. Then shuffle them. Then try to get the reproducible shuffled order using tf random set seed and a combination of seed. And then figure out, just see what happens. If in doubt, run the code. You can't break it. So have a practice of that. And I'll see you in the next video. We'll see a few other ways to make tensors. In the last video, we went over the concept of shuffling the order of elements in our tensor. And we tried it out a few times, but we ran into some problems using the global random seed and the operation level random seed. But the main intuition behind shuffling the order of tensors is that if we were trying to build a food image classification neural network, and we had 15,000 images of food, 10,000 images of ramen, 5,000 images of spaghetti, and our neural network, all it saw was the ramen images first, the patterns that it learns may be too aligned with what's in a ramen image rather than a spaghetti image. So that's why we might want to shuffle the order of our images so that the patterns that our neural network learns are attuned to both kinds of images throughout the entire training cycle. So let's go back here. We also left off, last video was full on. We left off with an exercise to read through the TensorFlow documentation. Again, the first few times, or the first probably 100 times you read through the documentation, you might not fully understand it, but with a lot of practice, you'll start to get the concepts. And so what did you find? Did you try to create 5 random tensors and shuffle them? I'll tell you what I found. After reading these rules, number 4, I think, is what relates most to us. It says, if both the global and the operation seed are set, both seeds are used in conjunction to determine the random sequence. Okay, so if we come back here, if we set tf random.shuffle, we try to shuffle our, so this is the operation level seed. So if we run that, okay, we get a different order each time. But then, if we set the global random seed, what do you think is going to happen? So we'll go here, global level random seed, operation level random seed. Do we get the same order every time? 10, 7, 3, 4, 2, 5. 10, 7, 3, 4, 2, 5. 10, 7, 3, 4, 2, 5. Beautiful. We could keep going, but we're just going to trust that this rule is correct. So here, we come here. Let's write down here. It looks like if we want our tensors, or maybe our shuffled tensors, that's a better way of saying it, our shuffled tensors to be in the same order, we've got to use the global level random seed as well as the operation level random seed. And then we'll put in here, if you want to put in a quote, you can do this little arrow thing here. Rule 4, there we go. So again, now this might not make a lot of sense of why you want reproducible tensors, but as you start to run more deep learning experiments, you'll often find is that because a neural network initializes itself with random patterns, you could get different results every single time you run this experiment. So, to make reproducible experiments, you probably want to shuffle your data in a similar order, initialize with a similar random pattern, and then run through this experiment. But for now, just be aware that if you want to set the random seed, TensorFlow has a few rules that you have to adhere to in order to get reproducible randomness. Whoa, that's a bit of a tongue twister. So let's have a look at some other ways to make tensors. Other ways to make tensors. The first one is if you're familiar with NumPy, you can do NumPy 1s. What's this? NumPy 1s. Let's have a read. Return a new array of given shape and type filled with 1s. So for many NumPy operations, because NumPy is one of the most prevalent numerical computing libraries out there, TensorFlow has similar operations. So TensorFlow 1s creates a tensor with all elements set to 1. Okay, let's try that out. So tf 1s, what happens here? Let's check the doc string. Can we do that? Yeah, there we go. tf1s, it looks like we have to pass it a shape and then a data type. So why don't we make it 10.7? What happens? Wonderful. Create a tensor of all ones. And then we want to go maybe create a tensor of all zeros. Oh, how do you think we might do that? If we created a tensor of all ones, how might we create a tensor of all zeros? I wanted you to try and guess this before we even bother looking it up. Let's go tf zeros. And then what shape should we pass this under? So this is in square brackets. Shape you can also pass in curly brackets here, or the curved brackets. How you'd create a tuple. 3, 4, put a space there. Wonderful. Okay, so if we wanted to create a tensor of all ones and all zeros, we can do that using tf1s or tf zeros, very similar to NumPy. And another thing, speaking of NumPy, we might as well cover that while we're here. You can also turn NumPy arrays into tensors. Whoa, into TensorFlow tensors. So remember, the main difference between, well, actually, I don't think we've covered this, but actually, let's put this here. We want text, so I'm going to push Command MM. We'll go here, turn NumPy arrays into tensors. And the main difference between NumPy and TensorFlow, this should be NumPy arrays, is that tensors can be run on a GPU much faster for numerical computing. Otherwise, they're very similar. So let's try this out. We want to import NumPy as NP, and then we want to create NumPy A. This capitalization, often you'll see a matrix created with a capital, constant sum matrix, and then often you'll see a vector with a non-capital. So that's a little tidbit there too. So we'll put that there. And then we'll go little capital for matrix or tensor, non-capital for vector. So we want to make just a simple NumPy array. Range, dtype is going to be int. Actually, we'll make it int32. So this is going to create, you might be able to guess, so NumPy A range between 1 and 25. So create a NumPy array between 1 and 25. Let's have a look at that. NumPy A. Now, how do you think you might turn this into a tensor? So if we come back to our tf.constant documentation, creates a constant tensor from a tensor-like object, value. Okay, what's value? Where's the doc string for that? Value. A constant value or list of output type dtype. It doesn't really give us much, but let's try. If in doubt, code it out. A equals tf.constant. Do you think we can just pass our NumPy A, this one here, directly to tf.constant? I mean, what do you think is going to happen if we do this? Oh, wonderful. There we go. We've now just converted our NumPy array. So if we have a look here, the output here is an array that's of type NumPy. And then if we go here, we've just passed it to tf.constant. Now it's into the form of a tensor. How beautiful is that? So anything we've got in NumPy, we can convert to a tensor by just passing it to something like tf.constant. Now, what if we wanted to change the shape of this? So this is a shape 24. How about if we wanted to make it into a 3-dimensional tensor? Yeah, that sounds fun. So let's change it into 2, 3, 4. Is that the right? 2 times 3 times 4. Now, why do you think I checked that? We'll see in a second. Hey, look at that. Maybe we'll make this b equals tf.constant NumPy A. And then we'll go A, B. Ooh, so there's a change shape one. Our first one, A. We've got the shape modifier there. So this is 1, 2. So 2 is the first dimension. And then 3, 1, 2, 3. And then 4, 1, 2, 3, 4. Wonderful. But the unmodified shape is just the same shape as our original NumPy array, which is just 24. So this is a vector, and this would be a tensor because it's got more than one dimension. Now, the important thing to know about shape is that if you want to readjust the shape of a tensor or an array, the new elements here must add up to give the same number of elements in the original tensor. So what if we tried here? What's going to happen? It doesn't work. Eager execution of tf constants with unsupported shape. Value has 24 elements. Shape is 2, 3, 5 with 30 elements. So if we go here, that doesn't work. We go there. Wonderful. We need it to equal 24. So what about 3 times 8? Let's try that. 3 times 8. We're kind of getting a little bit ahead of ourselves here with this reshape. Oh, look at that. Beautiful. So 3 times 8 equals 24. So that works. So this is 1, 2, 3 rows. And then 1, 2, 3, 4, 5, 6, 7, 8. 8 elements per row. Beautiful. Okay. So we've seen how we can turn NumPy arrays into tensors, and we've seen how to create tensors with all ones and all zeros. It's probably time that we get a little bit more information from our tensors. So let's make that in our next video. So getting information from tensors. All right, so have a play around, create some NumPy arrays, turn them into TensorFlow tensors, and then try to adjust their shape so they fit into a different size. And then you could even check the number of dimensions of A. But otherwise, give that a go, and I'll see you in the next video. We'll see how we can get more information from our tensors. We finished up the last video checking out how NumPy arrays, which are a very common form of representing numerical data, can be used or actually also converted into tensors. And the main difference being between a NumPy array and a TensorFlow tensor is that although they may store the same information here, so this array here, NumPy A, has the numbers 1 to 24, and this tensor here, B, has the numbers 1 to 24, is that because this one's in a tensor format, it can run on a GPU, which we'll see later on in the course is a lot faster than a non-GPU chip at finding patterns in numerical data, that is. Let's have a look at how we'll get a bit more information from our tensors. But before we do that, I just want to show you a little tidbit. So I took a break after this lecture and came back to my notebook. And what happened was the runtime disconnected. Now you can't see it here, but we've got a green tick saying we're connected. But when you disconnect in Colab, you might find that, it's still there. But if the memory has gone, so for example, if we did A and it told us that A didn't exist, what I like to use is go to runtime and then run before. What this is going to do is run every cell before the current cell, meaning if we've instantiated some variables such as NumPy A, those variables are going to get reinstantiated and TensorFlow is going to get re-imported, etc. We don't necessarily need to do it now because, or in my case, because it seems that Colab has remembered my variables. But if you do come into that case, go runtime, run before, and as you'll see, all the cells here are going to run. Now they run pretty quickly. We get the same error we got before, but then we can just go Shift Enter, run, keep running down to where we were. And then all of the variables we've been working with will be reinstantiated. Wonderful. So with that being said, let's get back to our getting information from tensors. There will be times where you want to get different attributes of your tensors. Let's have a look. Let's have the following vocabulary at least. So we want shape. These are the most important tensor terms. Axis or dimension. And then you'll also want the size. So if we come here to our keynote, we'll have a look at how to do those in code in a minute. But if we go on to the next slide, these are some of the main tensor attributes here. So we've got shape, axis or dimension, and then size. And the meaning here, the shape is the length or the number of elements of each dimension of a tensor, and we can get that by going tensor.shape. The rank, the number of tensor dimensions. For example, a scalar has rank 0 or 0 dimensions. A vector has rank 1 or 1 dimension. And a tensor has rank n or n dimensions, where n can be almost any number, 0 and above. And then we can get that by going tensor.ndim. We've seen that a few times. Axis or dimension. So this is how you access a particular dimension of a tensor. For example, if we wanted to index on the first dimension, tensors are 0 index, so the first dimension is actually 0, 1, etc. And then if we wanted to get all of the elements in the 0th dimension and then the 1 axis, we can use some indexing like this. We'll see this in a minute. And then if we wanted the size attribute, the size is the total number of items or elements in a tensor. And we can access that by using tf.size. So let's go back. When dealing with tensors, you probably want to be aware of the following attributes. Boom. Shape, axis, rank, size. I said that out of order, but that doesn't really matter. So probably the most important one here will be shape, but we'll see that again in practice. Let's create a tensor. Create a rank 4 tensor. Now, if I say rank 4 tensor, if we come back here, what does that mean? Rank, the number of tensor dimensions. So what might that look like? We want 4 dimensions. We come in here, we want rank 4 tensor equals tf.zeros. What does tf.zeros do? This is a little test from before. We just covered this one. 2, 3, 4, 5. So remember, this is probably the shape parameter here. So rank 4, we've got 1, 2, 3, 4 dimensions here. Now let's have a look at this rank 4 tensor. Beautiful. Now this is all zeros. So if we see here, this is 1. So this is the first axis. This is 1, 2. Then the next one is 3. So we've got within the 1 and 2, we've got 1, 2, 3. Now this will take some getting used to. The only reason I'm able to sort of deduce which is which of these elements here is because I've had a lot of practice writing different tensors. Now if we look at 4, within the 3, so 1, 2, 3, we've got 1, 2, 3, 4. And now we've got 5. So within the 4, 1, 2, 3, 4, we've got 1, 2, 3, 4, 5. Now, as we'll see later on, I know I keep saying later on, we're getting the fundamentals down pat here, is you'll probably spend most of your time dealing with lining your shapes of your tensors up. When you pass a tensor into a neural network, it typically has to be in a certain shape, and then the output tensor that comes out of a neural network, so in other words, the patterns a neural network has learned, the tensor again has to be in a certain shape. So it's good to be able to deduce different elements of a tensor by its shape. So if we wanted rank 4 tensor, let's get its 0th element. What does that look like? Which is this 3 tensor here. So see how we've indexed onto this second shape here? Now the shape changes because we're getting this set of 3 here, this set of 3 tensors. And so the shape here is 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5. Again, it'll take quite a bit of practice to get used to that, but that's just a brief overview. Now, what we might do is get all of the shape, the rank, axis or dimension, and the size of our tensor. So we just saw the 0th axis. Let's go rank 4 tensor.shape. You might be able to guess what this is already. Rank 4 tensor.ndim, so the number of dimensions. And then let's get the size of our tensor. Before I even type any of these, you might be able to deduce what they actually are already. So what's the shape? Probably going to be similar to what we set the shape as. The ndim, remember that's the number of dimensions in our tensor. And the size is what, if we come back to our keynote? The size is the total number of items in the tensor. Out of all of these, I think size will probably be the one you use least often, but I'm just putting it here for completeness. So if we go there, boom, So we look, these come in order again. So the shape is 2, 3, 4, 5. Yep. The number of dimensions is 4. That makes sense because there's 1, 2, 3, 4. Beautiful. And then the size is there's 120 elements. Now, what might that be? I'll give you a hint. 2 times 3 times 4 times 5. What do you think this is going to equal? 120. Beautiful. Okay. How about we print out some various attributes of our tensor, make them a bit more readable. So I want to show you, get various attributes of our tensor. This is what I often do to sort of create pretty, I call this pretty print statements. I mean, there is a function called pretty print, but when I'm trying to figure out or visualize my tensor data, I typically set up a bunch of print statements like this, especially when I'm inspecting the outputs of a neural network. So print, so I want to get the data type of every element. Boom, that's what I want. And then I want to get the number of dimensions, which can be the rank. And again, typing this stuff out is tedious when you first do it, but it does help visualize. I mean, we could put this into a function if we wanted to later on. Print, and now how about the shape of our tensor? That's going to be rank for tensor.shape. I'm not sure why that disappeared. Beautiful. And then now, how many elements are along the 0th axis? So elements along the 0 axis. Oh, axis doesn't have that. And we want to go rank for tensor 0 dot shape. Oh no, maybe we want shape 0. That's what we want. And then how about we want elements along the last axis. So I want rank for tensor shape. Now -1 we can use for the last axis. So instead of, we have 1, 2, 3, 4 here, we could have used 3 because it's the 4th index, but we're going to use -1 just to grab the last index. That's a little trick for Python indexing. And then we want to go the total number of elements in our tensor, which will be tf size rank for, is this going to autocomplete? Rank for tensor. That should be ready to go. Let's have a look. What do we get? Okay, data type of every element. D type is a float. So, okay, that makes sense because we've got 0 dot, yeah. Number of dimensions, rank 4, yes, that makes sense, 1, 2, 3, 4. Shape of tensor, yes, we've seen that before. Elements along 0 axis, so 2 elements there, yeah, beautiful. Elements along the last axis, 5, that's correct, wonderful. And the total number of elements in our tensor is tf.tensor 120, oh, NumPy 120. Now that output can be a little confusing, so I want to show you just a trick to convert it into a NumPy integer. So you can just go here. With the tensor output, for a lot of them, you can just add .numpy on the end, and we'll watch the conversion here. So this is there, or actually we might do it with and without, just so you can see the difference. I'm just going to copy that line. Boom. There we go. So the total number of elements in our tensor, that's it coming out as a tf tensor type. But if we add the numpy on the end, we get it in this single element, which can be handy if you didn't want to have the tf tensor type. You just want the element itself. Try using .numpy at the end there. All right, wonderful. Since we now know a fair few pieces of information on how to get them from our tensors, we'll practice. One very important thing is being able to index on tensors. So we'll do a little bit of practice of that in the next video. So I'll see you then. So in the last video, we checked out how we can get various attributes from any tensor that we can create, such as the data type, the number of dimensions, the shape, and then various other attributes of it, which can be helpful when we're trying to figure out just what's going on with our tensors. Because, I mean, although we can see this one, oftentimes with neural networks, you'll be dealing with tensors that you can't actually visualize, meaning that they're so big that you won't be able to just look at them. So you need to be able to use code to find different information or different attributes about them. So now let's have a look. Say we did have a tensor like this, and we want to index it. So the beautiful thing about tensors is that, oh, we don't want that. I just want to turn that into text. So we'll go here, indexing tensors. So tensors can be indexed just like Python lists. So if you've ever done indexing on Python lists, we'll see how it relates here. But if not, that's okay, because we're just going to get hands-on as we do. That's the theme of this course. So get the first two elements of each dimension in our tensor. So if you have had experience with indexing Python lists, how do you think you might get the first two elements of each dimension of our rank 4 tensor? So remember, we've got 1, 2, 3, 4 dimensions here, and we want the first two elements. In our case, it's going to be 0 for every single one of them, but we want the first two elements of each dimension. So give that a try. If not, I'm going to start writing the code to do it, and we're going to have a look at it in a few seconds. So this is how I would get, or how you would index a tensor to get the first two elements of each dimension. There we go. So just like a Python list. So if we make here sum list equals 1, 2, 3, 4, and we want the first two elements of sum list, we go here. Use the colon, we'll get 1, 2. Beautiful. So now we can do the same, but with our tensor, we just have multiple dimensions. We separate them by column. So let's have a look at what the output of this is. Wonderful. Because our tensor is all zeros, we get 2, 2, 2, 2, and each value is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. But can you see the shape here? This is the first, the outer tensor. This is the second one on the 0th dimension. And then we have 2 here, 1, 2. And then we have 2 within these brackets, so 1, 2. And then the final two, the elements within the most inner brackets. So 0, 0. Again, takes a lot of practice, but just look at these diagrams and start to count the tensors yourself of tensors that you can visualize. As a warning, if the tensors are too large, it'll probably separate them with 3 dots, but we'll get to that in a bit. How about if we wanted to get the dimension, or get each dimension from each index except for the final one? Now, does that make sense? So we want get each dimension from each index except for the final one. Oh, sorry, that doesn't make sense. Get the first element from each dimension, from each index except for the final one. Okay, how might we do that? Actually, let's try it with our sum list. If we wanted the first element, 1. Beautiful. Now, we want the first element from every dimension except for the final one. So let's try that. Rank 4 tensor, and we want first element from each dimension except for the last one. Will that work? We don't have the last one there. Let's try. Wonderful. 1, 1, 1, 5. Beautiful. So that means all of our tensors kind of get flattened. All the other shapes get flattened into 1, but we've still got 5. Beautiful. We can get the same thing if we add this colon here. So this colon, if it's there without a number, it just means get the whole thing. So there we go, same output as before, 1, 1, 1, 5 for the last dimension. Now if we wanted to change this up, say we wanted the, except for the second last one, what do you think this is going to output? If we go here, rank 4 tensor, if we want to get the second last axis, and we go shape. So we're getting the first element from each dimension of our tensor except for the second last one. So what shape is this going to output if we run this line? Let's try. Wonderful. So there we go. 1, 1, 4, 1. Again, plenty of practice, but that's how we're going to learn things. So there we go. 1, 3, 1, 1. And then we could do the same here with the 0th axis. Beautiful. Okay, we'll convert that back so that comment there makes sense. Now, what else might we want to do? If we've got our tensor of this shape, sometimes what we might want to do is expand or reshape. So in this case, we've seen a little bit before on how to reshape a tensor, but let's practice changing or adding an extra dimension to the end of a tensor. So how about we create a rank 2 tensor, which has how many dimensions? 2 dimensions. So we can do that by rank 2 tensor. You can pause the video here if you want and try to create your own rank 2 tensor without me coding. But we want tf.constant, my favorite numbers, 10, 7. And then how about 3, 4, because 3 and 4 add to 7. And now let's have a look at our tensor, rank 2 tensor. We could even get some attributes about it. Rank 2 tensor, ndim. Again, lots of practice here, figuring out information about our tensors. Okay, the shape 2, yep, ndim, that's exactly what we want. Now, if we wanted to get the last item of each row, of our rank 2 tensor, how might we do that? So again, let's remind ourselves what it looks like. Rank 2 tensor. Let's remind ourselves what our Python list looks like, sum list. How do we get the last element of a list? Sum list -1. So there we go. So if we want to get the last item of each row of our rank 2 tensor, well, the row comes first, so row, column. So we might go, rank 2 tensor, so the last item, -1. Does that make sense? Let's see. Does that get it? So 7, 4. Beautiful. That's what we want. If we wanted to add an extra dimension onto this shape here, so maybe we have 2, 2, 1, we can do so in 2 ways. And now this is helpful for later on when we're creating neural networks and we need to alter the size of our tensors so that their shapes line up. So might not seem like it's very helpful now, but I just want to sort of plant the seed so that when we come across it in future videos, it's not like, whoa, Daniel, we haven't covered this method before. So let's go in here, add in extra dimension to our rank 2 tensor. So we want to turn our rank 2 tensor into a rank 3 tensor, but keeping the exact same information that is stored in our rank 2 tensor. So we're not going to change these numbers. We're just going to change the shape that the numbers fit into. And we can do that by going here, ... Now this is a little bit of fancy notation. You might not have seen this before. We can go tf.new_axis. Let's see what this does. Oh, we need to visualize our tensor, don't we? Beautiful. So you see what that did there? That's now added a dimension on the end of 1. So let's look this up, tf.new_axis. tf.tensor. If we search, again, I'm just pressing Command F, you might press Control F, tf.new_axis. There we go. So 1 of 8, it appears 8 times. So insert another dimension. Does it have the actual definition here? Notes tf.new_axis is none as in NumPy. So if you're using NumPy, you probably use none. In TensorFlow, it's tf.new_axis. It doesn't actually say what it does. Sometimes where you'll find the documentation, it can be quite hard to sometimes find the exact definition of this method, but you can kind of deduce what it does by running through the examples as we see here. So let's go in there. It's better off just to remember, if in doubt, write the code, try it out. So the other alternative to using this, oh, by the way, these 3 dots means on every previous access to this one. So this means instead of just going like this, so see how we've got access 0, access 1, access 2 in this case, add an access on the very end. We can just scrap these and go every access before the last one, include those because that's ... and add a new access on the end. So the other alternative to tf.new_axis is alternative to tf.new_axis. You might also see tf.expand_dims. So that stands for expand dimensions. And then we're going to pass it rank 2 tensor. And then we want to expand it on the final axis. So -1 means expand the final axis. There we go. We get the exact same output as this notation here. It's just slightly different. So if we want to go here, tf.expand_dims. There we go. We got some documentation for this one. So we have the input. We come down. It says, what is the input? The input is a tensor and the axis is integer specifying the dimension index at which to expand the shape of input, giving an input of d dimensions. So if we come back here, what do you think will happen if we go axis equals 0? So look at our shape there. What I might do is keep that there. We're going to retype this out. tf expand dims rank to tensor. We want as much practice as writing TensorFlow code as possible, right? So expand the 0 axis. So let's try that. Boom. So now, instead of being on the end, our extra dimension is at the front, and then we can even change it. We want the extra dimension in the middle. Wonderful. And then if we want to put it on the end, we can go -1. Beautiful. So we might put that there. Expand the 0 axis. And so notice, even if we run this and we check out rank 2 tensor, the numbers inside stay the same, 10, 7, 3, 4, except the dimensions change. So how those numbers are stored changes. We've covered a fair bit in terms of getting information from our tensors and also indexing our tensors. Now let's have a look at how we might. We've actually done a little bit of manipulation here too, but the next videos we might go through manipulating tensors. In other words, known as tensor operations. So if we do have elements within our tensors, how do we manipulate those and how do we combine them into different ways? So go back through, practice expanding the dimensions of tensors, practice getting different attributes from tensors that you've created. And then in the next video, we'll see what kind of tensor operations we can work with. If your data is stored in some sort of tensor format, finding patterns in those tensor formats often involves manipulating tensors. Now, again, when building models in TensorFlow, much of the pattern discovery within tensors is done for you. However, oftentimes that pattern discovery is through the extended use of a few basic operations. So let's start getting into those, otherwise known as tensor operations. We'll start off with basic operations. Now, do we have a tensor? So you can add values to a tensor using the addition operator. And by the way, when I say basic operations, I'm talking about the default Python operators such as plus, minus, multiplication, and then if we want divide, we can go like that. Right, so we can add values to a tensor using the addition operator. So let's create a tensor equals tf.constant, and we might make it 10, 7, my favorite, and 3, 4. And now if we go here, plus 10, what do you think will happen? So this is our tensor here. And if we just use the basic operation of tensor plus 10, wonderful. We get 10 plus 10 is 20, 7 plus 10 is 17, 3 plus 10 is 13, and 4 plus 10 is 14. Wonderful. Now you'll notice that the original tensor is unchanged. This is important because when we're manipulating tensors, we don't necessarily always want to change the underlying tensor. The only way it'll change is if we go tensor equals tensor plus 10. We'll reset it. Now this is going to be plus 20, isn't it? There we go. We'll come back here. There we go, tensor. But if we got rid of this, tensor, we rerun this cell. Oh, invalid syntax. And then we rerun this one. We still get the same values as what our original tensor was. And we might just press enter there so it's more succinct with how it comes out. Beautiful. So, of course, other operations also work. So multiplication also works. So if we wanted to go tensor times 10, same thing. We get 100 because 10 times 10, 100, 70, 30, 40, etc. And then subtraction if you want. So tensor minus 10 can go into the negatives. That's no problem. Tensors can store a whole range of different values. In addition to the operators, like the Python operators, we can also use an equivalent TensorFlow function. Now, what this means is that if we do use the TensorFlow function, so that means we're accessing the TensorFlow library. Let me just show you, because it's easier to talk about something if we can see it. We can use the TensorFlow built-in function too. So tf.multiply, and we want, see here, we get the doc string here. We get tf.mat.multiply, so we'll have a look at that in a moment, but I just want to demonstrate it to you. Tensor 10. We get the same output here. So if we go here, let's look up tf.math.multiply. So for a lot of these tf.math functions, so tf.math, we can do the alias of just tf multiply. So if we go tf multiply, it's just going to lead us to the same thing. Wonderful. Now, does it say here what the benefits are? It doesn't quite. But what I'm going to get you to do is just trust me here when I say that if you have to do some sort of tensor operation like this, and again, usually a lot of these will be done behind the scenes for you. But if you want your code to be sped up on a GPU, typically it gets sped up when you use the TensorFlow version of some sort of operator. So if we wanted to do addition, I mean, this is going to be very fast because it's only a small tensor. And we could do tensor plus 10. But if you want to have the advantages of TensorFlow built into your basic operations, use the tf math something tensor to manipulate your tensors. But here, again, even though we've used the TensorFlow function here, the original tensor is still unchanged. So these are the basic operators. Create some tensors, have some practice at running the addition, minus, multiplication, and division on them, and also do the equivalence of tf.multiply or tf.addition or something like that. Is it tf.addition? tf math addition? Or is it just add? Yeah, add. Okay. That's your little homework for this brief video here. But in the next one, we're going to have a look at a very important concept in neural networks, and that is matrix multiplication. We'll see how to do that with tensors. So we left off in the last video figuring out how we can manipulate our tensors with the basic operations. And so hopefully you've tried out a few of these for yourself. But now we're going to go on to matrix multiplication. So in machine learning, matrix multiplication is one of the most common tensor operations. So the ones we've been through already, these basic operations, are often referred to as element-wise operations. So that means that if we go here, for the addition, for example, we've got our tensor here, which is 10, 7, 3, 4. Now, element-wise means go through one element at a time and just add 10. So this element, add 10. This element, add 10. This element, add 10. This element, add 10. But there's a few different types. So matrix multiplication and the dot product are not necessarily element-wise. So if we go here, what is matrix multiplication? How to multiply matrices. Math is fun. I really like this domain name, actually. Let's have a look here. A matrix is an array of numbers. To multiply a matrix by a single number is easy. So 2 times 4 equals 8. Yes. That's what we've done, right? So that's element-wise. So 2 times 0 equals 0, 2 times 1 equals 2, 2 times -9 equals -18. Beautiful. However, what if we wanted to multiply a matrix by another matrix? And remember, because we're using TensorFlow, even though this is a matrix, we're referring to them as tensors as well. So I want you to read this as matrix and tensor interchangeable. But to multiply a matrix by another matrix, we need to do the dot product of rows and columns. What does that mean? Let's see an example. So the dot product is the first row and the first column. Okay, so we've got a row here times this column equals 58. Okay. The dot product is where we multiply matching members, then sum them up. So 1, 2, 3 times 7, 9, 11. Okay, 1, 2, 3 times 7, 9, 11, yes. Equals 1 times 7. Okay, yeah. 2 times 9. Yeah, 2 times 9. 3 times 11. Okay, I've got that. That equals 58. Then we do it again for the second column, and that's 64. And then again. a great website I like to visualize this is, I believe, matrix multiplication.xyz. We'll go to that. So here, beautiful. We can even customize these. So we'll go here, 1, 2, 7, my favorite number, 7, 2, 1, just to be fancy. And then maybe 3, 3, 3, because I like 3 as well. And then this can just stay the same. So might zoom in here. So let's go multiply. What happens? Whoa, we get some. So that tensor just came up there and jumped on top of that. And then if we go through, we go 1 times 2, 2 times 6, 7 times 1. Okay, so that's 2 plus 12 plus 7. How did this get to 21? 2 plus 12 plus 7. We might try a different set of numbers. How did that work? 5. Maybe our matrix multiplication demo is busted. Multiply. Let's try. 1 times 3 plus 12 plus 5. Does that make sense? So 3, 12 plus 5. Yeah, that makes sense. 15. So this is 3 plus 12 is 15 plus 5 is 20. There we go. And if we step through there, step through, step through, wow, we get the output there. Before we even start to write code, go to this website, start practicing around, see what happens. And after you've done that for about a minute or so, or maybe 3 minutes, give yourself a few different goes. Let's go back to the notebook and see how we can do this exact operation in TensorFlow code. So I'll give yourself a second there, but I'm going to start coding so you can pause the video now if you want, try out that website and come back. So let's see matrix multiplication in TensorFlow. What if we just Google that, matrix multiplication in TensorFlow? matmul, there we go. tf.linalg, which is short for linear algebra, .matmul. Multiplies matrix A by matrix B, producing A times B. A, B. And we get a whole bunch of documentation, which is beautiful. We could read through that, or we could write the code ourselves. So, what do we have? Do we have a tensor? Print our tensor. We can print it if we want. Print, yes we do. Now tf matmul. Now for a lot of these operations, you can usually drop the intermediary here. So linalg. This is a little trick of TensorFlow. You can just do tf.matmul, which is what I'm about to do here. tf.matmul, tensor, tensor. Can we matrix multiply those? Oh, yes, we can. Wonderful. We get 121, 98, 42, 37. Beautiful. Now, if you wanted to do the matrix multiplication, Python has an operator, A. Now you see how the outputs here actually are different to if we just did, what if we did tensor times tensor? We get different outputs here. Okay. Because if we have a look at our tensor again, this is element-wise. So it's just gone 10, maybe we'll print it out twice. 10 times 10 is 100, 7 times 7 is 49, 3 times 3 is 9, 4 times 4 is 16. Whereas with matmul, we've gone in this fancy little way here. So maybe, I've got an idea, we recreate this tensor. That could be a little exercise for you as well, is to recreate this tensor in TensorFlow and recreate this tensor in TensorFlow. So the same elements in the same shape. This would be a what? 1, 2, 3, a 3 by 3 tensor. And this would be a 1, 2, 3 by 2 tensor, so 3 by 2. And then run tf.matmul on left tensor, right tensor. See if you get the same outputs as here. But we come back here. If you wanted to do matrix multiplication with a Python operator, we can do tensor at tensor. So the at symbol in Python actually is for matrix multiplication. Now, Both of these examples work because our tensor variable, this is an important fact. This is where we come in and we check the shapes attribute. Because our tensor.shape attribute is 2 and 2. So both of them have the same shape of 2 and 2. But what if we wanted to do matrix multiplication on tensors which had differing shapes? Now, rather than just think about it, let's try. So create a tensor of maybe 3, 2. Similar to this one here. So this is 3, 2. Remember, rows come first. 1, 2, 3. Columns, 1, 2. Let's create a similar one. Create a 3, 2 tensor equals tf.constant. And we want 1, 2. We'll keep this one nice and simple. 3, 4, 5, 6. Beautiful. And then we want create another 3, 2 tensor. And in this case, it can be y, tf, constant, and we'll just increase this one. So that can go from 7, 8, 9, 10, 11, 12. Wonderful. Let's have a look at both of those. X, y. Okay, so we've got two tensors here, both of the same shape, 3 by 2, and they got slightly differing elements. Now, what if we tried to matrix multiply them? So let's try to matrix multiply tensors of same shape. We could do it like that. See what happens. Oh, matrix size incompatible. In 3, 2, in 3, 2. What if we try the TF map mall? What happens here? X, Y. Invalid. Matrix size incompatible. Same thing. 3, 2, in 0. So this is our first element here, our 0th element. And this is our other element here, our first element, which is also 3, 2. This is where we have two rules for matrix multiplication. Do these websites tell us? Why do we do it this way? Actually, this is a great example. I'm going to put this as an external resource if we come back. If you ever see this emoji in the course, this is a resource. So resource, info, and example of matrix multiplication. So check that out. If you ever see that little book emoji, that's an external resource that I definitely recommend. Now, let's go back to here. Why doesn't this work? I don't think this web page explicitly states it, but I'm going to tell you anyway. You can look this up. You'll find this wherever you find matrix multiplication, is that there is a couple of rules that our tensors or matrices need to fulfill. So come up here. Let's put in here. There are two rules our tensors or matrices need to fulfill if we're going to matrix multiply them. Now, rule 1, the inner dimensions must match. And rule 2, the resulting matrix has the shape of the inner dimensions. So knowing these two rules, I'm going to set you a challenge. Is before the next video, we're going to go through these two rules and see how we can fix our problem here. But considering these two tensors, so we've got, if I say rule 1 is that the inner dimensions must match, what are the inner dimensions here? Maybe 2 and 3, they don't really match. So how would we get the inner dimensions of these two matrices to match? That's your challenge. If you're not sure, that's completely fine, but that's your challenge before the next video. If you can get it done, amazing work. If not, we're going to go through that in the next video. So I'll see you there. In the last video, we kind of left off on an error. And we said in this video that we're going to fix it. So let's do that. Now we tried to matrix multiply two tensors of the same shape, specifically x and y. They're both of the shape 3, 2. We've got this little error here saying in 0 is 3, 2 and in 1 is 3, 2. So matrix size incompatible. So if we come up here, back to the rules we set ourselves, the inner dimensions must match. And the resulting matrix has the same shape of the inner dimensions. Now, if you had a go at fixing this and you got through it, excellent work. You may want to skip over this lecture. However, if you didn't make it, that's completely fine. Matrix multiplication takes a little while to get your head around. If we come over here, I've got a slide. Matrix multiplication is also known as the dot product. So when we call the code tf.matmul, and we have a matrix of some size here and a matrix of some size here, remember, a lot of the operations that we do can be on matrices or tensors of an arbitrary size, but just for illustration purposes, I've done this size here. So here's our first rule. So numbers on the inside must match. And there's our second rule. New size is the same as outside numbers. Okay. So if we come back, does that line up with what we've said here? The inner dimensions must match. The resulting matrix has the same shape of the inner dimensions. Oh no. Of the outer dimensions. There we go. Getting our own rules incorrect. So we come back. Let's have a look at what's going on here. We've got tf.matmul. We've got one matrix or tensor here, A, B, C, D, E, F, G, H, I, which is the shape of 3 by 3. Wonderful. And this will run because the numbers on the inside match. See these two 3s here with the red background? And this is of shape 3, 2. So 1, 2, 3, and 2 columns. Okay, so that matches. And then we're going to result in here. If we did the dot product, which is the same as matrix multiply in TensorFlow, we have A times J plus B times L plus C times N, and then we follow through with that rule for every single cell in these two, or every single element in these two tensors. And now the new size is 3 by 2. 1 row, 2 row, 3 row, 2 columns, which is the blue numbers here. Okay, wonderful. And then if we swap these elements from letters to actual numbers, so the same shapes here, we take 5 times 4. Okay, this is the same as A times J. Yes. 0 times 6. Okay, 0 times 6. Yes, which is the same as B times L. Wonderful. And then we have 3 times 8. Which is the same as C times N. All right. Now, again, looking at these diagrams, they're quite, for the first, I would say, 20, 30, 50 times you look at dot products and matrix multiplications, it takes a lot of repetition to get used to. But then if we have 5 times 4 equals 20, plus 0 times 6 equals 0, plus 3 times 8 equals 24, so we add these 3 up, we get 44 in the top left. Repeat the same for each element, and we get this resulting matrix here. Now, the live demo we've already had a look at. Matrix multiplication.xyz. This is what's happening here. If we reset and multiply, we take that, we flip it on the top, then we go here, we get 20, and we get the next 2 elements, and the next 2, and the next 1. So this is a moving diagram of what's going on here. So let's go back to our code. Let's fix it up. Let's make it work. So knowing our 2 rules, number 1, that the inner dimensions must match, and that the resulting matrix is the same shape as the outer dimensions, how might we get this to work? Well, we're either going to have to change the shape of this matrix or change the shape of this matrix. Again, I'm using the term matrix and tensor interchangeably here. Or we're going to just have to create an entirely new tensor with the same shapes on the inner axes. So let's see it in action. Let's change the shape of y. So we can change a shape using tf.reshape y, and then we enter the shape that we'd like. In our case, it is currently 3, 2. So maybe we change it to 2, 3. And let's see what happens. Ooh, wonderful. Let's see the original y. Beautiful. So we can see that the 9 has come up to here in this one, and we've now got 10, 11, 12. So this has got 2 rows and 3 columns. Okay, so maybe we go try to multiply x by reshaped y. So x, and we might have to put matrix multiply here so we know what type of multiplication we're doing. X, tf, reshape, y, and then shape 2, 3. Now you see what's happening here? So if we remind ourselves what shape x is shape 3, 2. Let's pay attention only to the shapes. tf.reshape y shape equals 2, 3 dot shape. Paying attention to our rule that the shapes of the inner dimensions, so this tensor multiplied by this tensor, the inner dimensions must match. Does that rule get fulfilled? To me it does, because we've got an inner dimension of 2 here and an inner dimension of 2 here. Let's test it out. Beautiful. It looks like that worked. So we come here, we want to make a new cell. What if we tried to use tf.matmul on this? So if we go tf.matmul x tf.reshape, and then we want y shape equals 2, 3. Is this going to work as well? Beautiful. Now we get the same outputs there. Now hold on. Now do you think if we were to reverse this, it would work as well? Now I mean we reshape x to be a different shape instead of reshaping y. If in doubt, code it out. So x tf reshape x, we're going to change that to be 2, 3 this time. And we're going to not change the shape of y. Let's see what happens. Ah, what happened there? So let's see. We'll just put a little note here. Try change the shape of x instead of y. So you see here how this one has the shape 3, 3, but this one has the shape 2, 2. That's because in this operation, we multiplied two tensors with the shape 3, 2 and 2, 3. So the resulting tensor finishes with the dimensions of the outer dimensions. Whereas in this case, if we go tf.reshape x, shape equals 2, 3, y dot shape, we also want the shape here. This is our other rule of matrix multiplication. Because we reshaped x, the resulting matrix here ends up in a shape of 2, 2, because it becomes the outer dimensions. So see here, back to our rule, numbers on the inside must match. New size is the same as outside numbers. Okay, so in both these cases, depending on which tensor we reshaped, the matrix multiplication works, but the resulting output is different. Now, that's a very important point. When you're dealing with matrix multiplication or dot products, it really depends on which tensor you manipulate in terms of what your output would be. So see here how different these two outputs are? Again, we're multiplying the same numbers, but just in different shapes. So that's an important concept to be aware of. And now, we can do the same thing with reshape as with transpose. So let's have a look. This is another important tensor transformation. So can do the same with transpose. However, as you'll see in a second, transpose is slightly different to what reshape is. So transpose, and if we do tf reshape x, shape equals 2, 3. So this is the transpose tensor. They're the same shape as reshaping it. However, you'll notice with the transpose is that, well, let's get x, the first one as well. It starts off as 1, 2, 3, 4, 5, 6. Then the transpose is 1, 3, 5. The odd ones are up the first row. And then 2, 4, 6. And then the reshape is 1, 2, 3, 4, 5, 6. So the difference between transpose and reshape is that transpose flips the axes, whereas reshape just shuffles the tensor around into the shape that you want. So if we go here, TensorFlow transpose, tf transpose, here we go. Transpose A, where A is a tensor. Wow, that's a great description. Permutes the dimensions according to the value of perm. The return's tensor's dimension I will correspond to the input dimension perm I. If perm is not given, it is set to n minus 1 to 0, where n is the rank of the input tensor. Hence, by default, this operation performs a regular matrix transpose on 2D input tensors. Okay, so we see here 1, 2, 3, 4, 5, 6, transpose. Now the shape is 3, 2. Again, we could try a bunch of different examples, but let's go back and write some different code here. So what we might want to do is, because transpose also changes the shape of our X tensor, let's try matrix multiplication with transpose rather than reshape. So tf map mul tf transpose X and Y. What might be the output here? Let's find out. 89, 98, 116, 128. Now see how that is different here? Now that is because transpose flips the axes rather than shuffles around the elements of a tensor. This can be quite confusing. However, this kind of data manipulation is a reminder that you're going to spend a lot of your time in machine learning and neural networks reshaping your data in the form of tensors to both prepare it to be used with various operations such as feeding into the model, and once you get it out of the model, to be able to deduce patterns from it and convert it into something human understandable. Now, again, the numbers that we're dealing with are just basically toy numbers. To see an example of how matrix multiplication is actually used, this is a great example. This may seem an odd and complicated way of multiplying, but it is necessary. I'll give you a real-life example to illustrate why we multiply matrices this way. So, example, the local shop sells 3 types of pies, and then we have details here. And if you go through this, this is actually a dot product to work out the value of sales for any given day. Now, this is just a small example here, but in the case of neural networks, they're actually going to go through an absolute multitude of these different numerical transformations to find patterns in our data. The good news is, most of the time, is that once we've set up our neural network code, once we've gotten our tensors into the right shape, a lot of these are done behind the scenes for us. So, with that being said, let's finish this video here. And in the next video, we'll go through a little bit more. We'll really cement down, or we'll get some more practice with transposing and reshaping different matrices and practicing matrix multiplication. So I'll see you there. We've had a little bit of hands-on practice with matrix multiplication and transposing and reshaping different tensors. We're going to do one more video on it to really nail it down. So let's call this one the dot product. And we want to turn that into a markdown cell. Beautiful. So let's go here. Matrix multiplication is also referred to as the dot product. And now you can perform matrix multiplication using, we want tf.mapmul matrix, which is short for matrix multiplication, or we can do it with tf.tensor. We haven't seen this one yet, but they essentially do the same thing, just with different parameters. So we come here. We've also gotten hands-on with matrix multiplication using matrix multiplication.xyz, and we've seen this colorful example of the dot product. But let's once again get a little bit more hands-on with some code. So let's see how we might use tensor dot. Again, I'm spelling tensor wrong. I'm going to do that throughout this whole course, aren't I? There we go. So perform the dot product on x and y. Now this requires x or y to be transposed. We've also seen how transposing results in different outputs than reshaping. And transposing is flipping the axis, whereas reshaping is just reshuffling. So if we come here and if we reset this, I want you to have a guess at what type of operation this is. Is this a reshape if I go like that and flip it? Or is that a transpose? I'll give you a hint. What did we do? We had to flip the axes to get it up like that. So in that case, it's going to be a transpose. Now, let's use tf.tensor dot. And actually, before we do that, Let's remind ourselves of what x and y are. X is a tensor of shape 3 and 2, and y is a tensor of shape 3, 2. They have increasing elements from 1 through to 12. Beautiful. Now, if we go tf transpose x and y, oh, I've typed y as a mini case. There we go. Tensor dot, oh, missing argument axes. So we want to type in on the first axes. Beautiful, 89, 98, 116, 128. Now if we look up tf tensor dot, what is this going to tell us? Tensor contraction of A and B along specified axes and outer product. Tensor dot, also known as tensor contraction, sums the product of elements from A and B over the indices specified by A axes and B axes. Now again, you can read through this if you'd really like to, or you can practice coding it. I would suggest doing both. Now, in this case, you might notice that we could use transpose or reshape. However, we get different results. Now, let's try matrix multiplication by transposing y and reshaping y. We've done it with x. Let's try it with y. So, perform matrix multiplication. There's going to be a lot of repetition when manipulating tensors because we want to get practice. Y transposed. So tf matmul, let's take x and we'll transpose y. Transpose, there we go. Now perform matrix multiplication between x and y reshaped. tf.matmul. You might be wondering why I'm just continually showing you different ways of manipulating matrices. It's because you're going to spend a lot of your time reshaping tensors and matrices into the shape that you want them. So if we can get as much hands-on experience as we can, it might not mean too much to us now because we're just working with toy data. It means later on down the track when we have to reshape and manipulate our tensors and matrices, is that we've got all of this practice under our belt. Wonderful. So we see we get different results from transpose and reshape. Now, to really demonstrate the fact here, or the fact that calling reshape and transpose on y don't necessarily result in the same values, is that we're going to go through the same steps we did up here before for x. But let's make it a little bit more pretty. So check the values of y. This is how I really try to understand things. And transposed y. So if I am writing some code, as I've said before, and I'm wondering why I'm getting different outputs of my tensors and the calculations that I'm making aren't really sort of making sense in my head. By the way, this /n is for new line. As I've said, one of the most common errors you're going to get in writing neural network code is misshaped tensors. And even more like sort of just as common, but deceiving error that is when your tensors line up with shape, but the outputs that you're getting, so you get no error message, it just works. So it's important then to be able to investigate what's going on and figure out, that's called a silent error, is that when your code works, like no error gets outputted from the code itself, but the results just clearly aren't correct. So this is the sort of thing that I will do to investigate those silent errors. tf transpose y, that's what we want to do. So I'll create some sort of print statement like this, and then I'll use this to really get my head around what's going on. So this is our normal y, 7, 8, 9, 10, 11, 12, beautiful. Now this is reshaped, again just reshuffled. We bring the 9 up here, we move the 10 across, the 11 comes up there, the 12 goes on there, so 7, 8, 9, 10, 11, 12, beautiful. Now this is the transposed, so all we've done here is just flip the axes. Let's recreate this one, nice and simple. So 7, 8, 9, 10, 11, 12 over here. We'll just let that run through. This is a great way to just visualize. Let me reset this. 7, 8, 9, 10, 11, 12. Okay, we come back to this tab. You see how we've just got the same tensor here, 7, 8, 9, 10, 11, 12. This is the same over here, beautiful. Now watch, This is a transpose. We're going to bring this up, flip it, boom. That's what has happened here. You see? Except this one is upside down in this case. So it just displays it slightly differently, but the shape and where the values end up in this case is what's going to happen if we were to write, say, some code like this. So if we go tf.mapMul x tf transpose y. Beautiful. There we go. So this is a sort of investigative work that we do. We've had a fair bit of practice now transposing and reshaped. If you're still unclear what the difference is between transpose and reshape, or you're wondering, which one should I use? Well, most of the time, these operations will be done behind the scenes for you. So if you write neural network code, it's going to do a lot of matrix multiplication behind the scenes to figure out different patterns in numbers. What sort of patterns are they? Well, remember, here's a simple example of the kind of patterns you can work out with matrix multiplication. But again, it'll be different depending what problem you're working on. But generally, whenever you're performing a matrix multiplication on two different tensors and the shapes of the matrices or tensors don't line up, you will transpose one of the tensors rather than reshaping them. So I'll write that here. Generally, when performing matrix multiplication on two tensors and one of the axes doesn't line up, you will transpose rather than reshape one of the tensors to satisfy the matrix multiplication rules. Alrighty. So again, if there's anything that doesn't quite stick out or make sense, I would definitely encourage you to create a whole bunch of different tensors. Try to use tf.mapMul on them. Try to use tensor dot if you want, or try to even use the @ operator between them. Generally, if we're using TensorFlow, we're going to be using mapMul. But get some errors, fix the shapes with transpose and reshape, and see what kind of different outputs you get. So we've covered matrix multiplication. Now let's have a look at, if we've got the default data type is often int32. So sometimes, depending on what data we're working with, the data type might not be int32. So what if we had to change the data type of a tensor? That's what we'll look at in the next video. I'll see you there. All right, so as we said in a previous video, the default data type of most tensors will be int32, depending on how they've been created. However, sometimes you'll want to change the data type of your tensor. So let's see how we'll do that. So we can create a new tensor with the default data type, which is float32. Yeah, let's start off with float. Now, I just said that the default is int32, but if we go, the default data type will actually depend on what data is inside your tensor. So if there are floats inside your tensor, we will have b.dtype tf.float32. Now if we create c equals tf.constant, now in here we want 710, and this is going to be c.dtype int32. Wonderful. So in the current version of TensorFlow that I'm using, which is TF, I believe it's 2.3 version, 2.3.0, you may have a slightly different version depending on when you're watching this video. At this time, if we create a tensor with floats inside it, they're going to be a float32 type. And if we create a tensor with integers inside it, they're going to be of tf.int32 type. Now, let's say if we wanted to change from float32 to float16. Now, this is called reduced precision. Let's go 32-bit precision. What does this mean? So I'm reading a book about OpenGL ES development. A float in Java has 32 bits of precision, while a byte has 8 bits of precision. This might seem like an obvious point to make, but there are 4 bytes in every float. Okay. So that's in Java. That's not what we want. So 32-bit precision tensor versus 16-bit precision tensor. Mixed precision. Here we go. TensorFlow. Why did we ever doubt the TensorFlow documentation for having something? Mixed precision is the use of both 16 and 32-bit floating point types in a model during training to make it run faster and use less memory. Okay. By keeping certain parts of the model in 32-bit types for numeric stability, the model will have a lower step time and train equally as well in terms of evaluation metrics such as accuracy. Using this guide, this API can improve performance by more than 3 times on modern GPUs and 60% on TPUs. Today, most models use float32 D-type, which takes 32 bits of memory. There we go. However, there are 2 lower precision D-types, float16 and bfloat16, each which takes 16 bits of memory instead. Beautiful. Modern accelerators can run operations faster in the 16-bit D-types. Okay, so the main takeaway from this is that in TensorFlow, the default is 32-bit precision, right? However, we can also do, with modern pieces of hardware, we can also do float16, which takes 16 bits of memory instead. And modern accelerators, which are talking about hardware accelerators, so when we run our code on hardware, can run operations faster in the 16-bit D-types. That is what's exciting. So, in our case, if we wanted to change our numbers from 32-bit precision, in other words, storing this tensor in 32 bits on memory, we wanted to change it to float16, how might we do that? Well, let's have a look. We can use tf.cast, and then we're going to pass it our original tensor, and then its new D-type is going to be tf.float16. Oh, and then we want to do b, find out b. Wonderful, D-type equals float16. The original b, what we might do is type out b, and then b.dtype. So we'll reinstantiate b up here. Or maybe it's better just to go d here. Yeah, that's a better idea, Daniel. Wonderful, look at that. We got float32, and now d is the same as b, but it's been stored as float16. So, again, might not matter too much for tensors of only 2 elements, but if we had a tensor of 1,000,000 elements and we reduced the floating point size from 32 to 16, we've basically halved the amount of space our tensor is taking up on memory, allowing a hardware accelerator to make calculations on it, potentially twice as fast. Now again, that scale may be different because there's a lot of different things that go into computing scale and speeds and whatnot, but that's the concept I want you to imagine, is that although these numbers here take up less space on memory, they may be able to compute faster. And the same thing goes for if we wanted to change from int32 to float32, we can do it in a very similar manner. So let's go change from int32 to float32. So we can go e equals tf.cast. Which one do we make? C D-type equals tf.float32. Now let's have a look at e. Beautiful. So C was originally, there we go, D-type equals int32 and 710. We just changed it using tf.cast. So E is now, take C and turn it into a float32. Beautiful. And now we can take E float16 equals tf.cast E D-type equals tf.float16 E float16. Wonderful. So there are many different data types in TensorFlow. So if you ever come across the need to change your data type of a tensor because some calculations aren't working correctly, tf.cast is going to be your friend. So with that being said, let's have a look in the next video. We're going to go aggregating. We'll see what that means. So have a play around with this one. Create some tensors of float type, of integer type, and then change them from, you can go from float32 to float16, or you could go from int32 to float32. See how many different combinations of data type you can create and change before we see how we can aggregate our tensors. Welcome back. Now, after the last video, I took another little break. And so what you see here is when the cell numbers are empty. I just want to show you this. This is, rather than going straight onto the next video in practice, I just want to show you how I actually work with Google Colab notebooks every day. Is that when you leave it for a while, all your information in Colab is going to shut down so that Google's compute resources can be allocated to other people who want to use Colab. So you see here, I haven't got a connection. But if I decide to run a single cell, Shift and Enter, it's going to allocate some memory to me. Basically a computer in Google's warehouse full of computers somewhere around the world. And once it's ready to go, boom, we're connected. However, if I try to run this cell above here, TF is not defined, so I haven't imported TensorFlow. So what I often do is, we saw this in a previous video, but it'll work better now because see here, we've got 0, 1. These are the first cells I've tried to run in this notebook since taking a break. Let me do, if I wanted to run, I could do restart and run all, so that would run all the cells in this notebook, or I could just do run before, which is what I usually do. It's going to try and run all of the cells before whichever current cell that you're on. But boom, we get our type error right back up the top here, where we created our changeable tensor with tf.variable, and we deliberately caused an error. So if that happens, your errors are not going to fix themselves, but then we can just go back to here, and then we should be able to run all of our cells. I'm just continually pressing Shift and Enter. Should be pretty quick because we're not processing much data here, but we'll go right down to where we were, aggregating tensors. Oh, we got another error, that's all right. We'll keep going. Oh, we've covered a fair bit of ground here. Are we at? Yes, here we are. So we're back to where we were. So aggregating tensors. Now, let's have a look. What does aggregation mean? Define aggregation. A group, body, or mass composed of many distinct parts or individual. A galaxy is an aggregation of stars and gas. The collecting of units or parts into a mass or whole. The condition of being so collected. Well, that doesn't really help us with understanding tensors, but we're going to see hands-on what aggregation means in the concept of, or in the topic of tensors. So to me, aggregating tensors equals condensing them from multiple values down to a smaller amount of values. That's how I conceptually understand aggregation. You can create your own definition, and in fact, I actually want you to start doing that more and more with, as you get more familiar with the world of deep learning, is to, of course, there's going to be agreed upon definitions in the field, but I also want you to start conceptualizing your own definitions in a way that you best understand things. But let's see how we might start aggregating our tensors. The first way we're going to do is by getting the absolute values. So this is actually probably not the best form of aggregation to start with, but we're going to include it here anyway, just for completeness. So we create a tensor. What were we up to? E. We might recreate D here, tf.constant, just because Daniel begins with D, and it's, aside from the number 7, D is probably my favorite. Sorry, number 7 is probably my favorite number, and D is probably my favorite letter. So fun fact about me. There we go, get the absolute values. Beautiful. So, we just created a new tensor, and if we wanted to get the absolute values, we can go tf.absd, and we'll see what this does. Beautiful. So the absolute values are basically just take all the negative numbers in one tensor and turn them into positive numbers. So if we see here, let's check out the docstring. I'm pressing Shift, Command, Space to get this docstring. Computes the absolute value of a tensor. Given a tensor of integer or floating point values, this operation returns a tensor of the same type where each element returns the absolute value of the corresponding element in the input. Beautiful, such a formal definition. And then we've got some example use cases. So let's actually start to see a few more versions of aggregation. Let's go through the following forms of aggregation. We'll turn that into a markdown cell, and we'll come down here. The first one I want to go through is get the minimum, and then we might want to get the maximum of a certain tensor. We might want to get the mean of a tensor, and we also might want to get the sum of a tensor. Now, I've shown you a few different ways of how you can explore different methods in TensorFlow. So if you wanted to start with a tensor and find the minimum, the maximum, the mean, or the sum, how might you research? So if we go here, find the mean of a tensor in TensorFlow. Here's a little hint. If you were to search that, you can pause the video now, skip and go ahead and try to create your own tensor, do these 4 things, and then come back and we'll compare notes, all right? But otherwise, if you're going to watch on, let's start by creating a random tensor so that we can practice each of these 4 things here. Create a random tensor. We might create a larger tensor. Yeah, how about we do that? With values between 0 and 100 of, how long should we do it? Of size 50. Let's do that. So E equals tf.constant. We'll do it using a NumPy random array. So again, this is going to just be return random integers from low inclusive value to high exclusive value. So we can just go 0 to 100, size equals 50. Now this should give us a tensor. Beautiful. 50 values between 0 and 100. And we might go how do we check the size of our tensor? Let's practice. And then how do we check the shape of our tensors? And then how do we check how many number of dimensions our tensor has? Beautiful. So we get size is 50, beautiful. The shape is also 50, and the number of dimensions is 1. All right. Now, how about we start with finding the minimum? So we're going to go find the minimum. To find the minimum of a tensor, you can do reduce min, pass it a tensor. Put the output there. Now, this is going to be a little bit of a trend with TensorFlow aggregation, is that the reduce underscore, in some, like NumPy, if we did np min, I believe, we can just go 0. But TensorFlow tends to put reduce underscore min in front of its aggregation methods here. So we'll get rid of that one. So knowing that this is the way to find the minimum, how do you think we might find the maximum? Let's find it anyway. Find the maximum. TF reduce max. Wonderful. So there's 97. So that makes sense because we have values between 0 and 100. So our lowest value so far is 0, and the highest value is 97. And find the mean. Let's go TF reduce mean of E. And wonderful. So 48 is about the average. So get the sum of a tensor. Let's have a guess. Find the sum. TF reduce underscore sum of E. And there is the sum of our tensor. Beautiful. Now, there's a few other things that we can do, such as I'm going to put a little challenge here. I want you, of our E tensor, before the next video, I'm going to put a little emoji here. Exercise is to, with what we've just learned, find the variance and standard deviation of our E tensor using TensorFlow methods. So if you're not sure what variance and standard deviation are, this challenge has 2 sides to it. First, you have to find the code to find the variance of our E tensor, and then you have to look up what variance and standard deviation are. So go and give that a try, and I'll see you in the next video. We finished up the last video with a little challenge. So did you figure it out? Did you find the variance and standard deviation of our E tensor using TensorFlow methods? I hope you gave it a try, but if not, we're going to check it out here. So find the variance of our tensor. Now, as you might have guessed, we can do tf reduce var e. Oh, has no method reduce var. Is it variance? Has no method reduce variance. Oh, TensorFlow variance. I typed TensorFlow wrong. Ah. Okay, we can do the reduce standard deviation. Have I led you on a wild goose chase? Yes, I totally meant for all this to happen. TFP. So what we might need to do is, what's TFP? This is what I like to do, is just figure out, go down the rabbit hole. TFP, TensorFlow probability. Okay. How do we import it? Can we do import TensorFlow probability as TFP? There we go. And then we might do tf.stats.reduce variance of E. What was that method again? We come back here. This is the type of research I want you to start practicing. Okay, tf.stats.variance. There we go. Wonderful. Okay, so there's the variance there. I'm going to put here, won't work. And then if we wanted to find the standard deviation, so let's put a little note here actually. To find the variance of our tensor, we need access to TensorFlow probability. And then we go here, find the standard deviation. See, I thought that you would be able to just do reduce variance. So I've learned something there too. Apparently, we need TensorFlow probability to find the variance. Now, I believe we can find the standard deviation here. Reduce STD. Ah, what's happened here? TF math reduced STD. Does it not have an alias? What if we do tf.math.reduce STD? Must be either real or complex. So if we come here, input tensor. What's wrong with our tensor? Reduces input tensor along the given axis. Unless keep dims is true, the rank of the tensor is reduced by 1. Input tensor, the tensor to reduce, should have real or complex type. Does it have to be a float? This is a good little challenge. I'm glad I issued this exercise. We can work this out together. So where's our, here, dtype int 64. You know what I think this method might need? Is if we cast our E tensor as dtype tf int 32, this might work. Int 32. Input must be real or complex. Maybe float 32. There we go. Okay. So this is what I mean. Things may not be as they appear when you go through the TensorFlow library. So up here, we've got a few relatively easy methods compared to what we had to do here. But this has been a great practice as to how you might go about researching and trying things out to make something work. So if you ever get that error that we got just before, let's write this again. So tf math.reduce std e for our tensor. So type error. If you ever get the type error message, come to the documentation, which is what we did here. All right, so there's tf math reduce std. And check out the types that they're using in the example workflows. So see here, the reason why I picked up that we might need to change our tensor to data type float32 is because they're using floats in their input sample here. So there we go. Returns the reduced tensor of the same D type as input tensor. Note for complex or complex 128 input, the return tensor will be of type float32 or float64 respectively. So usually, a lot of the time when you're working with TensorFlow, float32 is generally sort of the standard type throughout the entire library. So if you need to change the type of your tensors, chances are it might have to be in float32. But that was a good practice in exploration. Now in the next video, let's see how we're going to find the positional, maximum, and minimum. You might want to try this out now that you've had your expert problem-solving skills upgraded in this video. See how you might find the positional maximum and minimum of a tensor. I'll see you in the next video. So I was all ready for this video to jump straight into finding the positional maximum and minimum. However, after a little bit more exploration of the TensorFlow documentation, which can be a bit of a beast to tame, I found that we didn't actually have to jump through some of the hoops we did in the last video to find the variance. So look at this. I thought that we might just be able to go tf.reduce variance. It turns out we can find the variance of our tensor in a very similar way than what we've done here, finding the standard deviation, which is strange because with these methods, you can get rid of the math, but with the variance and standard deviation, you require the math. And so we've both learned something here. So I want to just show you here, if we want to go find the variance of our E tensor, we go tf.math.reduce variance, E, just exactly like we've done here in the documentation. And if you're ever stuck, you can just go through the documentation here, like tf.something, and just read up all the different methods. I mean, we're working with tf.math, so you might want to even try a fair few of these just to see what happens with what you're working on. But anyway, let's go back here. We'll find the variance. Input must be real or complex. How did we fix that? We'll go tf.cast. Let's change this D type to tf float32. And, oh, we forgot a little bracket on the end. Wonderful. We get a very similar number up here to our variance that we found using the TensorFlow probability. So, turns out we actually don't need access to TensorFlow probability. However, what we just went through was a great exercise in figuring things out. I mean, at first you'll try something and it might not work, and then you'll find a fix to it. Then you'll find that, hey, the fix probably wasn't even the best way of doing it. We did a little bit more research and we found we wanted to find the variance without inputting any other libraries aside from TensorFlow. We can just do it like this. But anyway, let's get into finding the positional maximum and minimum. Now, when might this be helpful? Well, you're going to see this a lot when your neural network outputs prediction probabilities, which we haven't seen yet. But if we go here, so remember our little example where we got our images, we input it into some numerical encoding, goes through our neural network, finds the patterns in there, adjusts its random weights that it initializes with, it updates its representation outputs. And then here, oftentimes the representation outputs are referred to as prediction probabilities. So in this case, 983 is the highest number, 0.04, 0.013. So imagine if above here, if this column was, say, ramen, and this column was, say, spaghetti, and this column was, say, not ramen or spaghetti. So in this case, this number, the highest output, this is our ramen column, would be dedicated to ramen because the first index here, the 0th index, the highest number goes to ramen. And then if we wanted to turn this row into labels, we might go ramen, spaghetti, not ramen or spaghetti. Which one has the highest value? The index where spaghetti occurs. And then for this one, which is no food, so ramen, spaghetti, no food or spaghetti, this is the highest number. So we might want to get this index. So that's what I mean by finding the positional maximum minimum. At which index of the tensor or of this row does the maximum value occur? So in this row, it occurs at the 0th index. In this row, it occurs at the 1st index. And in this row, it occurs at the 2nd index. But let's have a look how we might do that in code. So the first thing we're going to do is create a new tensor. So create a new tensor for finding positional minimum and maximum. We go here, f equals tf random. We'll create a random tensor with uniform this time. We'll give it a shape of, we'll get it 50 long. Let's have a look. Beautiful. Now I wonder if we go here, tf random set seed equals 42. Do we get the same numbers? So this one is, you help me remember what's this first number, 6645621. Okay, beautiful. So if you use random seed 42, you should get the same numbers as me. Don't worry too much if you don't, if something's changed between now and when you watch this video, but we just need a tensor with 50 random numbers and we can work with this. So if we wanted to find the maximum element position of f, meaning at which index does the maximum value occur? So I'm going to guess, let's have a quick look. There's 948. Can we beat that? Yes, we can. There's 967. So that'll be about, maybe 43. Let's try. TF. So find the positional maximum. Now, the positional maximum is often referred to as argmax. So I believe it's the same in NumPy, mp.argmax. If we wanted to find the docstring here, returns the indices of the maximum values along an axis. Same with argmax. Returns the index with the largest value across axes of a tensor. So let's do it. Let's put in our 42. Oh, so we were close. Now, if we were to index on our largest value position. So what I mean by this is if we grab our f tensor and then we find argmax f, what value are we going to get? Boom, it's that value there. And then if we go find the max value of f, tf.reduce max f. Do all these values line up? Wonderful. So this should, now let's check for equality just to be safe. If we go argmax tf, argmax f, does this equal, we might put a little assert here, because this will error if they don't equal. No error. And then if we take away this assert, we should get true. Beautiful. So this is we're indexing. Does this make sense that they are equal? Because look, we found the positional maximum, which gives us position at index 42, which is this one. That's the maximum value of this tensor. And then we can index on our largest value position. So it's saying, hey, take the f tensor and grab position 42, or grab the value from position 42, which is this. Yes. Now, if we use just our reduce max method, which is saying, hey, find me the max value of f, we get this value, and then we check to see if they're equal. Beautiful. Now, another one you might use, I don't use this one as often, is finding the minimum. So wherever the positional minimum occurs in here, can we find it? There's 0.03, that's pretty low. So maybe it's that one. Or there's 0.009. So I'm guessing that might be at, let's go 21 or 20. So find the positional minimum. We want to do TF, you might be able to, if argmax finds the maximum, what do you think finds the minimum? If you guessed argmin, 100 points for you. Boom, so position 16, let's find out what it is. Find the minimum using the positional minimum index. So f, tf, argmin f. 0.009. So that was actually 16. There we go. So that's index 16. Beautiful. Alrighty then. So what we might do in the next video is we can see how we can squeeze our tensor. In other words, removing all single dimensions. So have a go at this. Maybe create your own tensor. Can be as big as you like. And practice around using the argmax and argmin methods to see if you can find the minimum, maximum positional values of your tensor. And I'll see you in the next video. How'd you go? Did you create your own tensor? Did you find the minimum and maximum positions? I hope you did. But for now, we are on to the next part, which is squeezing a tensor. Oh, we're going to give our tensors a big hug. In other words, removing all single dimensions. You're going to fall in love with tensors by the end of this course if you haven't already. Now, what we might do is, as always, we need to create a tensor to get started. Now, I might go here, G. Are we up to G? Yeah. E, F, G, H, I, J, K, L, M, N, O, P. I won't do that again. No promises, but I like to sing. Now, if we go here, what have we got? So I'm creating a similar tensor to what we did before, random uniform, but this time we're going to use the shape parameter to add a few single dimensions right to the start. So if we check G, look at this. So we have just, actually, let me use our faithful random seed as 42. Beautiful, we're getting the same numbers there. Yep, 6645, 621. Maybe I'll know that off by heart by the end of this course. And so we have here, the shape is what we have to pay attention to with squeezing. So this is shape 11150. So see here, we've got a few square brackets, 1, 2, 3, 4, and then the innermost square brackets is where the big dog 50 is sitting. Now, what we're going to do with squeezing, it's actually quite a fun little concept. So if we go G shape, we get that. Now, if we were to go G squeezed, that could be our TensorFlow wrapper name, G squeezed. TF squeeze, and now, actually, we'll check the doc string. Removes dimensions of size 1 from the shape of a tensor. Now, if I were to run this, what do you think G squeezed new shape is going to be? I'll give you 3, 2, 1 to guess, and now let's check. Boom. So there we go. So what squeeze does is, we just read that before with the doc string, but we'll read it again. Removes dimensions of size 1 from the shape of a tensor. So if your tensor has too many single dimensions and you want to just reduce it, so get rid of all these extra dimensions here and reduce it back to its essence, you can use the squeeze method. So that's a little tidbit there. Nice and quick video, this one. And the next one, we're going to cover one-hot encoding. So I'll see you there. Okay, so if you wanted to one-hot encoding tensors. Now, what is one-hot encoding? Let's check this out. What is one-hot encoding? If you've done any machine learning before, you might have come across one-hot encoding, but it's a very important concept in terms of preparing data. This is a great website, by the way, Machine Learning Mastery. So let's check what this says. There, okay. So this is a great example. We'll create our own in a minute, but let's just have a look here. So we've got 3 columns, red, green, blue. So row 2 has a 1 for red and 0 for the rest. So that is one-hot encoded for red. Row 3 has a 1 for green, but 0 for red and blue. So that is a one-hot encoding for green. And row 4 has a 0 for red, a 0 for green, and a 1 for blue. So that's a one-hot encode for blue. So that's a great way to turn, if we just remember, what do we have to do when we're passing our data to neural networks? We have to find a way to numerically encode it. One-hot encoding is a form of numerical encoding. So if we had the colors red, green, blue, and we wanted to pass it to our neural network, it would look at that and go, you know what? I'm very smart. I can find out patterns and numbers, but when you pass me words, red, green, blue, I can't understand them. So we could one-hot encode those words. Red could be 1 for red, 0 for blue, 0 for green, and so on, and then pass those as a tensor to our neural network. So let's have a look how we might do that in code. What we should do is create a list of indices. So values, pretend this is, let's get our sum list. Sum list can be 0, 1, 2, 3. In other words, maybe we go, could be red, green, blue, purple. And now, if we wanted to one-hot encode this, we can go one-hot encode our list of indices is tf.onehot sum list. We're missing one positional argument. All right, let's look up the docstring. What does this say? tf.onehot returns a one-hot tensor. If on value is not provided, it will default to a value of 1 with type dtype. Okay, where's the example? Here we go. For example, indices equals that, depth equals 3. We need to pass a depth parameter. Okay, so the output's going to be 3 pi 3 because this is 3 long and the depth is 3. So let's figure this out. Depth. If we have 4 elements here, what I've kind of given it away here, so pretend you can't see that. Well, it's going to be 4. Let's try it out. There we go. So do you see what's happened here? What kind of tensor we've created? We've transformed this tensor, sum list, into one hot encoded version of itself. So for the first row, this relates to the first element. So it's got a 1, as you see, for where 0 occurs, but then 0 for all of the other values. And now for this one, we've got this refers to this value here. It's got 0, yes, and a 1 because this is a number 1 here, and then so on for the other 2 values for each rows. Beautiful. Now, a fun little thing that we can do is that if we wanted to change this from, I mean, you're rarely going to use this in practice, but I want to show you anyway because it's cool. If you wanted to show, get rid of, rather than using 1s and 0s, we can use on value and off value and pass them different values. So let's go specify custom values for one-hot encoding. If we want to do tf.onehot, sum list, depth can be 4, and then on value can be, yo, I love deep learning. And then the off value can be, let's go, what could we do? I need something fun here. I also like to dance. Boom. Let's see what this comes out with. Oh, yo, I love deep learning. I also like to dance. 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 Yo, I love deep learning. I also like to dance. Did you know I like to dance? So have a practice with tf.onehot. Maybe create some of your own on values, off values. Again, rarely will you ever use them when you're passing them to a neural network because a neural network, what does it love? It loves numbers. But yeah, this is just a little fun exercise to practice one-hot encoding. Now, if we look up the tf.onehot, I believe it requires, so the indices, the indices have to be a tensor of indices. Okay, well, that makes sense. So yeah, go through the example there, create your own list of indices, and then one-hot encode it, practice around, see what happens if you change the depth parameter, and then change the on value and the off value. And I'll see you in the next video. Did you have some fun creating one-hot encoded tensors with different on and off values? I hope you did, and I hope you're loving deep learning. We actually haven't covered too much deep learning yet. We're still in the fundamentals, but I do believe you do like to dance. So by the end of this section, you're going to be able to dance through your way through TensorFlow code. And speaking of which, let's do a little bit more dancing through, there are some math functions. I just want to show you how to use a few more of these that you may come across. There's a lot here, as you see, tf.math overview. We've got a whole bunch here. But But let's practice with a few more. We can never get enough practice. We might go a few common mathematical operations, a squaring, log, and square root. So let's see how we'll do that. First things first, let's create a new tensor. So this time we might go h, I believe we're up to. So tf, I'm going to show you a new way to create a tensor. 1 to 10. Nice and simple. Oh, let's see it. There we go. Now, if we want to square it, how do you think we might do it? tf square h. Beautiful. So we get just the square of all that. So 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, etc., etc. And then if we wanted to find the square root, let's find the square root. We come over here. Maybe we go square root. Will this show us? There we go. TF math square root. Beautiful. Let's try that. Now, I believe it may have an alias. We can just skip the math part. Oh, what do we got here? Invalid argument error. Value for attribute t of int32 is not on the list of allowed values. Okay, this is good. So again, we're coming across a value error where it's saying that int32, is that the type of our tensor? Yes, it is. Int32 is not in the list of allowed values for this function. So we want b float, half float, double, complex 64, complex 128. Okay, let's change it into a float. tf.cast, and the D type is going to be tf.float32. Oh, forgot again. Boom! Look at that. There we go. Actually, let me put this one above here so that you'll know for future reference, is that this is going to be will error. Method requires non-int type. So if we put here just h, we get an error. Wonderful. How about we find the log? So we go here, find the log. Now, again, TensorFlow, oops. We want to go up here and search for log. tf math log, wonderful. Computes the natural logarithm of x element wise. Has it got an alias? I'm pretty sure we can skip the math part, but if not, we can try it out. So find the log, tf log of h. Has no attribute log. Oh, do we need math for this one? We do. Oh, again, we get the same error as above. So what do we have to do here? Value for t of int32 is not on the list of allowed values. What do we have to do? I'll give you a hint. We have to turn it into a float, or at least one of the allowed values. We've got some rules here. So we go here, tf.cast h dtype equals tf.float32. Will this work? Wonderful. There we go. So that's just an example again of how many different functions you're going to find in TensorFlow, and a little bit of practice again, as I can't stress this enough, is how much practice we're going to need sort of just making sure our tensors are in the right data type. So have a play around with some of the functions in tf.math and see how many of them, pick 3 and try them out. The ones that we haven't covered so far, and see if you come up against any errors like this, what you can do to fix them. So that's a little challenge before the next video. We've covered a whole bunch so far. We've even seen before how tensors can interact with NumPy arrays, but let's have a dedicated session on tensors and NumPy. So if you've done any numerical computing before or any type of data science or machine learning, you've probably used NumPy. So if we come here, what is NumPy? Not going to dig too much into this because we want to get focused on using it. But chances are, there we go, the fundamental package for scientific computing with Python. So NumPy is a fundamental library for any type of numerical computing with Python, and it's all built upon the NumPy array. So TensorFlow interacts beautifully with NumPy arrays. And we can see an example of that by, if we create a tensor, this is what we've seen before, directly from a NumPy array. So if TensorFlow is built upon the tensor, NumPy is built upon the array, and the beautiful thing is that they basically have full interoperability. I believe that's a word. That's like a fancy word for they work together quite nicely. So there we go. We create an array here, and then we pass it to tf.constant to turn it into a tf.tensor. Beautiful. And now we can convert it back from a tf.tensor to a NumPy array. So convert our tensor back to our NumPy array by just going np array j. And then we can check the type here by going type np array j. There we go. So np array j turns it into a NumPy array, and then when we check the type, it turns into a numpy.nd array, which is NumPy's base type, just like TensorFlow's base type is tf.tensor. All right, and we can also do the same thing as the cell above by convert TensorJ to a NumPy array using, if we go j.numpy, we've also seen the NumPy method in Tensor before as well, .numpy. And then if we check the type, j.numpy, we go here. Beautiful. So we can convert it back to a NumPy array there. Now, where this might be helpful is sometimes if you have, say if we have, let's rewrite j to be tf.constant, it's just a single number there. If we wanted to have access it just as the float on its own, we can actually do .numpy. And there we go. That'll give us access to it there. And if we want to go there. So the beautiful thing about being able to really easily convert our tensors to NumPy arrays and NumPy arrays into tensors is that if there's some sort of functionality that we want to use with that doesn't work with our data in tensor types, we can convert it to a NumPy array and use it there, and vice versa. So if we delete that, let's see. There's one more thing you should know. And that's default types of each are slightly different. So if we want to create numpyj equals tf.constant. We'll create this directly from a NumPy array, just as we've done before. It's going to go np array, same as above, 3, 7, 10. Wonderful. And then if we want to go TensorJ equals just tf.constant, we'll create this one directly from a Python list, 3, 7, 10. Now, if we want to go check the data types of each, now we've had some practice doing this, so you might be able to know if we wanted to check the data types of NumPyJ and TensorJ, what might we use? If you guessed we use the dtype attribute, you'd be 100% correct, TensorJ. And if you didn't guess correct, well, that's all right, we get to practice. Boom. So there we go. So if we create a tensor from a NumPy array, the default type is float64, whereas if we create a tensor from a Python list or directly through TensorFlow, the default type is going to be float32. Now, the reason why this is important is because, remember, we actually had some errors up here where we had to change the type of our tensors from a certain data type to another data type. So this is where I want you to be aware is that if you do convert your NumPy arrays into tensors, they may have a different data type to compared to if you created your tensors directly from TensorFlow. So just be aware of that. One of the main issues you'll run into when computing with different tensors is different data type issues. So treat this as your heads up. But that's a quick reiteration of tensors and NumPy. Remember, NumPy is a fundamental package for scientific computing with Python, and chances are, when you're doing machine learning and deep learning, you're going to run into NumPy somewhere. So keep in mind, TensorFlow works beautifully with NumPy arrays and vice versa. In the last video, we checked out how beautifully TensorFlow interacts with NumPy, and I kind of just added a little tidbit here. Remember the key emoji? If I've picked up a little tidbit that you should be aware of, I'm going to include it here with this little emoji as a key. Get it? There's a key there because it's a key idea. Anyway, you might be wondering, why are we using differences like NumPy arrays and tensors look basically the same when they come out? I mean, if we print one of our tensors, we get the NumPy version of it at the end. Well, one of the main differences between a TensorFlow tensor and a NumPy array is that a TensorFlow tensor can be run on a GPU or TPU for faster numerical processing. So remember, if we look up a GPU, it's a graphics processing unit. There we go. A graphics processing unit is a specialized electronic circuit designed to rapidly manipulate and alter memory to accelerate the creation of images in a frame buffer intended to output to a display device. Oh my goodness. In other words, they're really fast at doing numerical computing. And then we also have a TPU, which is a tensor processing unit. So a tensor processing unit is an AI accelerator, application-specific integrated circuit ASIC developed by Google, specifically for neural network machine learning, particularly using Google's own TensorFlow software, which is what we're getting familiar with right now. How exciting. So if we come down here, this is what this lecture is all about. That was kind of a long-winded intro to how you can find access to GPUs. Boom. So if we wanted to use our tensors on a GPU, how might we do that? The whole time we've been connected to Colab, and if we look here, it says connected to Python 3, Google Compute Engine Backend, RAM, disk. I wonder if, how might we, let's go TensorFlow, check GPU usage. Let's see this. tf.test is GPU available. That makes sense. Returns whether TensorFlow can access a GPU. Deprecated. What is it? Where is it? Have we got config here? What if we search? I believe it's called list physical devices. Oh, what happened there? tf config. There we go. List physical devices. Return a list of physical devices visible to the host runtime. This is how we're going to check what type of device TensorFlow is running on. So tf config list physical devices, we could type that out, but I'm going to write that in. tf.config list physical devices. Does that need, is that a method? What comes out here? Okay, physical device name, CPU, device type, CPU. So right now, we're running on a CPU. So this is a central processing unit. Now, this is also a computer chip, very fast at doing numerical computing, but not as fast as a tensor processing unit or a GPU. I'll let you do your research in terms of comparison between CPU and GPU for numerical processing, but just for now, trust me, GPU and TPUs are much faster than CPUs, and we'll see this when we start to write neural network code. However, if we wanted to, we can actually pass GPU to this. It says none. So it's going to return a list of the physical devices available. And right now we have no access. So you might have seen this in the Introduction to Colab video, but if not, I'll show you how we can get free access to a GPU, which is beautiful on behalf of Google. So if we go change runtime type, now I'll just redo that again. Runtime, change runtime type. Oh, what does this little question mark say? More info. GPU availability. Let me zoom in here. What types of GPUs are available in Colab? The types of GPUs that are available in Colab vary over time. This is necessary for Colab to provide access to these resources for free. Oh, that is exciting. That means we get access to a GPU for free. So thank you very much to Google. The GPUs available in Colab often include NVIDIA K80s, T4s, P4s, and P100s. I'll let you check out which ones are, what the differences between those are. Essentially, the higher the number, the faster the GPU. So this one's the fastest. T4 is faster than a K. These are actually in order in terms of speed. So I believe K80 is still very fast compared to a CPU, but not as fast as a P100. There's no way to choose what type of GPU you want. But anyway, you can keep reading that. If I want to change the hardware accelerator, it starts off as none. So whenever you start a default Colab notebook, you're going to get no GPU. So Google can allocate, compute power isn't free. So if we want to use a hardware accelerator, we have to choose. We can choose a TPU if we want, which is even faster than GPU, but that requires a little bit more setup. For this course, we're going to be focused on GPU. If you want to learn how to use a TPU, there's a great TensorFlow guide on that. I'll let you research that in your own time. Anyway, we'll go to GPU. We're going to click Save. Then our runtime is going to actually reset. So if we wanted to run this cell, because our runtime reset, we don't have access to TensorFlow anymore. But that's all right. So if we go here, import TensorFlow as TF and run this, there we go. It shows that now we have a CPU and a GPU. That's what we're after. So if we go in here, just type in GPU. Wonderful. And we can also check it because it's using an NVIDIA GPU. We can use this little command here, which is called bang, to basically say run this on the command line. We're going to type in NVIDIA SMI. I'm not quite sure what SMI stands for. If you want to tell me in a message, that'd be phenomenal. But I just know that this is the command to check what type of GPU you're using. Wonderful. So we've got access to a Tesla T4 GPU with almost 16 gigabytes of memory, which is this is actually quite a fast GPU. We're not going to take full advantage of it just yet. It's running CUDA version 10.1, which is basically, we look up CUDA, basically a driver, Compute Unified Device Architecture, which is a driver that is a parallel computing platform and application programming interface API model created by NVIDIA. You can read the full Wikipedia article if you want. What it does is it's kind of the interface between the GPU and our TensorFlow code that makes our TensorFlow code run really, really fast. And so, one last note, this is actually probably going to be the last video of this TensorFlow fundamentals section. The note here and the important takeaway is you might be wondering, okay, I've set up access to a GPU. Now, how do I get my TensorFlow code to run on it? Well, the amazing thing is if you have access to a CUDA-enabled GPU, and in our case, since we're using Colab and we do have a CUDA-enabled GPU, well, guess what? TensorFlow will automatically use it whenever possible. So we haven't actually done anything too intensive in terms of finding patterns in data using our neural networks. But to find patterns in data, to discover what's in an image and create representation outputs like this, our neural network algorithms are going to have to do a lot of mathematical calculations. And we're going to be writing TensorFlow code to do those calculations. And the beautiful thing is, because we have access to Google Colab and a GPU, those calculations are going to be sped up as much as possible. So let's have a quick just overview of what we've covered. We started with Introduction to Tensors. We learned a whole bunch of different ways to create tensors. We figured out how to shuffle the elements of tensors. We even made tensors with other ways, with tf1s, tf0s. We learned about NumPy and NumPy arrays and tensors. We actually covered that twice because it's such a fundamental concept. We figured out how to get information from our tensors, index them, change the data type, aggregate them, find the positional max and minimum, squeeze them, one-hot encode them, square, log, and square root. And again, how to make our calculations extremely fast by having free access to GPU with Google Colab. Now, with that being said, we have a whole bunch of different tabs here. Although we've covered a whole bunch, we've barely scratched the surface of the TensorFlow library. I mean, you can look at it here. Look at that. There's too much here to cover in a single course. So there are, well, actually, the good news is we've covered the fundamentals, the building blocks of what you'll need to sort of start your journey with TensorFlow. We've probably actually done a little bit more than that. But anyway, there's going to be a couple of exercises in the upcoming video, as well as some extra curriculum mainly been just getting familiar with the TensorFlow documentation and trying out a few different things. So check out that lecture resource there. Go back through the material to solve those exercises, and I'll see you in the next section. But congratulations for getting familiar with TensorFlow. Give yourself a pat on the back. You have now passed the TensorFlow fundamentals section. Woohoo!